Have you ever had a moment that felt so perfect you wished you could pause it forever? Or found yourself staring at old photographs, wondering where all those years disappeared to? We've all experienced time as this relentless, one-way current sweeping us from birth to old age, from past to future, never letting us turn back. We set alarms, mark calendars, and watch clocks, all trying to measure something that feels absolute and irreversible. But what if I told you that this entire experience, this river of time we're all floating on, might be nothing more than an elaborate illusion, a trick played on us by our own perception? Physics has been quietly whispering a secret that challenges everything we think we know about time. The equations that govern our universe don't actually care which way time flows. They work just as well backward as forward. At the deepest level of reality, there might be no inherent arrow of time pointing from past to future. This isn't just philosophical speculation. It's a conclusion emerging from some of the most profound theories in modern science. From the strange behavior of particles at the quantum scale to the vast expansion of our cosmos, clues are mounting that our experience of time may be more about how we're built than how the universe actually operates. In this journey together, we're going to explore how cutting-edge physics could completely rewrite our understanding of time itself. We'll venture into the realm of entropy and disorder, dive through the looking glass of quantum mechanics, and examine theories that suggest time might be reversible, circular, or even entirely emergent from more fundamental principles. By the end of this exploration, you might find yourself questioning not just the nature of time, but the very fabric of reality as you know it. This isn't just abstract science, it's a frontier that could ultimately reveal whether our one-way trip through existence is truly written in the laws of physics, or if we've been under a cosmic deception all along. This feeling that time marches in one direction only isn't a modern invention. It's a puzzle that has captivated human thought for millennia. The ancient Greek philosopher Aristotle wrestled with the nature of time, pondering its connection to motion and change. He saw it as a measure of before and after, a fundamental sequence of events. But even then, the question of why that sequence only goes one way remained a profound mystery. For centuries, this was largely a philosophical debate. Then came Isaac Newton. He envisioned time as an absolute, universal river flowing at a constant rate throughout the cosmos, independent of anything else. This absolute time was a backdrop against which the universe played out, and its flow was assumed to be uniform and relentless. Yet, even Newton's powerful framework didn't explain the directionality. It described how objects move through time, but not why time itself seems to have an arrow. This deep-seated intuition about time's one-way street is embedded in our very language and culture. We speak of time as a flowing river that we cannot step into twice, or we visualize it as an hourglass with the sand falling inexorably from the top chamber to the bottom. We look at old photographs and feel a sense of irretrievable loss, a past that is fixed and unchangeable, while the future remains open and unknown. We remember yesterday with clarity, but we can only guess at tomorrow. This asymmetry is the very core of our experience. It feels as undeniable as gravity. The true paradox, the thing that turns this from a philosophical curiosity into a deep scientific mystery, emerges when you compare this human experience with the cold, hard laws of physics. Take the equations that describe how planets orbit stars, or how two billiard balls collide on a table. These fundamental laws, from Newton's mechanics to Einstein's relativity to quantum theory, are almost entirely time-symmetric. If you were to take a video of two planets gracefully orbiting their common center of gravity, and then play that video backwards, what would you see? You would see two planets gracefully orbiting their common center of gravity. The motion obeys the same laws in reverse. There is nothing in the physics itself that tells you which version is the correct forward direction. The equations work perfectly either way, so here we stand at the edge of a breathtaking contradiction. Our every waking moment is saturated with the undeniable feeling of time's arrow. The smell of coffee brewing, the aging of a face, the shattering of a glass that never spontaneously reassembles. Yet, the most fundamental rules that we believe govern our universe show a complete indifference to this direction. They paint a picture of a world where past and future are, in principle, interchangeable. This chasm between what we feel and what the laws say is one of the greatest enigmas in all of science. It forces us to ask a radical question. Is the arrow of time a fundamental property of the universe itself, or is it somehow a product of our own point of view, a story we tell ourselves based on how we are constructed to perceive a much more symmetric reality? So where do we find a potential source for time's arrow in a universe governed by symmetric laws? The answer, for over a century, has seemed to lie in a single, powerful concept from thermodynamics: entropy. Often described as the universe's measure of disorder, entropy provides what appears to be the most concrete arrow of time we have. This is enshrined in the second law of thermodynamics, a principle so robust it feels almost like a cosmic decree. It states that for any isolated system, one that doesn't exchange energy or matter with its surroundings, the total entropy can never decrease. It only increases or, at best, remains constant. This isn't a suggestion. It's a fundamental rule that dictates the behavior of everything from steam engines to stars. We witness the relentless march of entropy every single day in processes that are utterly irreversible. Think about an ice cube dropped into a glass of warm water. It doesn't stay a perfect, ordered crystal. It melts, its molecules spreading out and mingling with the water, increasing the disorder of the system. Now try to imagine that process happening in reverse. You would see water molecules spontaneously organizing themselves, leaping out of the glass to form a structured, frozen cube on the table. It never happens, or consider the classic example of a dropped wine glass shattering on the floor. The transformation from a single, beautiful, ordered object into a chaotic mess of scattered shards is a dramatic increase in entropy. The reverse, where every fragment suddenly leaps off the floor and reassembles itself into a pristine glass mid-air, is a scene reserved for special effects reels, not reality. These events have a clear before and after, a past and a future defined by the increase of disorder. This gives us a powerful and intuitive explanation for why we remember the past and not the future. The past is a state of lower entropy, a more ordered arrangement. The broken glass was once whole, the melted ice was once a cube. Our memories are themselves physical structures in our brains, and the process of forming them involves irreversible changes that increase entropy. We are essentially biological recording devices for the universe's growing disorder. But here's where the plot thickens, and where the work of a 19th century physicist named Ludwig Boltzmann becomes absolutely crucial. He provided a stunning reinterpretation of the second law, one that transformed it from a fundamental decree into a matter of overwhelming probability. Boltzmann realized that entropy is not about order in an aesthetic sense, but about the number of ways a system's microscopic components can be arranged while still looking the same to us on a large scale. A whole wine glass is a very specific, very unlikely arrangement of atoms. There is essentially only one way for those atoms to be arranged to form that specific glass. But a pile of shattered glass, those same atoms can be arranged in a nearly infinite number of ways and still look like a pile of shattered glass. A state of high entropy isn't necessarily more disordered. It's just vastly more probable because there are so many more ways to achieve it. This statistical view turns the arrow of time into something far more mysterious. The second law isn't a law that forces entropy to increase. It's more like a rule of thumb that says systems will naturally evolve from less probable states to more probable states. It's not that the universe forbids a shattered glass from reassembling. It's just that the odds of all those scattered molecules randomly coordinating their motion to leap back into the precise shape of a glass are astronomically, unimaginably low. So low that for all practical purposes we can consider it impossible, but not fundamentally impossible according to the underlying laws of physics. This introduces a breathtaking and slightly unsettling idea. The arrow of time might not be woven into the fabric of the cosmos. Instead, it could be an emergent property, an illusion that arises from our perspective within a universe that started in an incredibly rare, low-entropy state. We perceive time flowing from past to future because we are living in the aftermath of that initial state, riding the wave of probability as the universe explores the countless ways to become more disordered. From this viewpoint, the irreversibility we experience is not a feature of the laws themselves, but a consequence of our incredibly specific and unlikely starting point. It suggests that if we could step outside of our universe and view it from the outside, the distinction between past and future might completely vanish, leaving only a static, timeless block where every event simply exists. The flow we feel so intensely would be a story we tell ourselves, a narrative born from statistics and our particular place in cosmic history. This profound indifference to time's direction isn't just limited to the graceful dance of celestial bodies. It extends right down to the fundamental forces that govern reality. Consider the equations of electromagnetism formulated by James Clerk Maxwell. They describe how light travels through space as an oscillating wave of electric and magnetic fields. If you were to record a beam of light moving from a star to your eye and then play that recording in reverse, the mathematics would still hold perfectly. The reversed beam would simply appear as a wave converging back onto the star, a scenario that, while strange to imagine, violates no physical law. The same is true for the strong and weak nuclear forces that operate within the atom. The interactions between quarks and the decay of particles are described by equations that don't possess a built-in preference for past or future. This concept was championed and made beautifully clear by the Nobel Prize-winning physicist Richard Feynman. He proposed a revolutionary way of thinking about antimatter, suggesting that a positron, the antimatter counterpart to an electron, could be mathematically described as an electron moving backwards in time. This wasn't just a quirky analogy, it was a serious interpretation that highlighted the deep symmetry at the heart of quantum mechanics. For Feynman, the laws of physics are like a perfectly balanced set of scales. They have no mechanism to tell which way the arrow of time is supposed to point. The equations simply don't care. They provide a stage upon which events can unfold, but the script detailing the sequence of those events seems to be written by something else entirely. This leaves us with a staggering intellectual vertigo. We are beings for whom cause always precedes effect. We are born, we live, and we die in a strict, unalterable sequence. We could never witness a fire causing a match to be struck or a sound wave rushing back into a person's mouth to form a word. Our entire existence is built upon this irreversible causality. Yet, the most fundamental description of reality we have, the collection of laws that explain everything from the formation of galaxies to the bonding of atoms, presents us with a universe that is, at its core, ambivalent about this sequence. This creates a chasm between the world as we experience it and the world as described by physics. So if the bedrock laws are symmetric, the origin of time's arrow cannot be found within them. It forces us to look elsewhere for an explanation. The direction of time must be something that emerges not from the laws themselves, but from the specific conditions in which those laws operate. It's like having a set of rules for shuffling a deck of cards. The rules themselves don't dictate whether the deck becomes more ordered or more shuffled. That outcome is entirely determined by the initial state of the deck. If you start with a perfectly ordered deck and then shuffle it, it will almost certainly become disordered. But if you start with a completely random deck and shuffle it, it's just as likely to become slightly more ordered as it is to become more disordered. The arrow comes from the starting point, not the rules of shuffling. This shifts the mystery from the laws of physics to the initial conditions of the universe itself, suggesting that the reason we remember the past and not the future might be because our cosmos began in a state of incredibly low entropy, a highly ordered configuration from which everything else has flowed. So we're left with this remarkable conclusion that the arrow of time is not a feature of the laws themselves, but a consequence of our starting point. The universe began in a state of exceptionally low entropy, a condition of incredible order and specificity. This is the ultimate source of the one-way street we all experience. But this realization only pushes the mystery one step further, forcing us to ask the most profound question of all. Why? Why did the universe begin in such a peculiar, unlikely state? A state that seems to be the very foundation of our experience of cause and effect, memory, and the flow of time itself. This starting point is what cosmologists call the Big Bang. But we have to be careful with that term. It wasn't an explosion in space. It was the rapid emergence of space, time, matter, and energy from an unimaginably hot, dense state. And crucially, that state was not a chaotic mess. It was, paradoxically, a state of exquisite order. The early universe was incredibly smooth and uniform. If you were to look at the cosmic microwave background radiation, the faint afterglow of the Big Bang, you would see a nearly perfect blanket of heat with only tiny, tiny variations. This smoothness represents a state of very low gravitational entropy. It's like a billiard table that is perfectly flat, with all the balls racked in a tight triangle. This is a highly ordered, low probability setup. The natural tendency over billions of years is for that smoothness to break down. Gravity pulls matter together, forming clumps, galaxies, stars, planets. The billiard balls scatter across the table. The universe becomes more lumpy, more disordered, more probable. This is the gravitational engine that has been driving the increase of entropy and the arrow of time for over 13 billion years. This idea that time's arrow is a product of this specific initial condition is formally known as the past hypothesis. It's the proposition that the reason the past is different from the future is entirely due to the fact that the universe started in a past state of very low entropy. It's not a law of physics, it's a boundary condition, a statement about how things were at one end of time. This hypothesis is what gives direction to the statistical arguments of Boltzmann. It explains why we see cups shatter and never unshatter, because we are living in the aftermath of a highly ordered beginning, riding the wave of probability as the universe explores the countless ways to become more disordered. Without this low entropy start, the laws of physics would show no preference and time would have no consistent arrow. We would see occasional moments of order emerging from disorder, like a shattered glass spontaneously reassembling. Our memories and our sense of causality would be impossible. This leads us to a truly dizzying possibility. If the arrow of time is not baked into the laws of physics, but is merely a consequence of our universe's initial conditions, then it might not be absolute. It might be contingent. What if our Big Bang, with its specific low entropy setup, is just one possibility among many? This is where cosmology ventures into some of its most speculative and fascinating territories, like the concept of the multiverse. In some multiverse theories, our universe is just one bubble in a vast cosmic foam of universes, each with its own unique set of physical constants and laws. If that's the case, could some of those other universes have begun with different initial conditions, perhaps a universe that started in a state of high entropy? For observers in such a universe, what would time be like? It's almost impossible for our brains to conceptualize. In a high entropy beginning, there would be no clear arrow of time from the start. The universe would be in a state of maximum disorder from its inception. There would be no driving gradient for change, no statistical push from order to disorder. Cause and effect would be blurred. Beings in such a universe might not have a coherent experience of a flowing time at all. Their consciousness might be a jumble of fragmented moments with no clear sequence. Or consider a universe that undergoes a big bounce, cycling through contractions and expansions. If entropy somehow reset during the bounce, the arrow of time could reverse with each new cycle. Beings in one cycle would remember what to us is the future and find the past unknown. These aren't just science fiction fantasies. They are logical extensions of the idea that time's arrow is not fundamental but inherited from a specific, and perhaps not unique, starting point. By questioning the uniqueness of our beginning, we are forced to confront the possibility that the relentless, one-way flow of time is not a universal truth. It might be a local phenomenon, a story that is true in our particular cosmic neighborhood but not elsewhere in the multiverse. The flow of time, so central to our very existence, could be a contingent feature of reality, dependent on a single, special moment some 13.8 billion years ago. This doesn't make it any less real for us, of course. We are inextricably tied to that initial condition. But it does suggest that the true nature of time might be far stranger and more malleable than our everyday experience could ever suggest. But if the arrow of time seems to falter when we look at the cosmos as a whole, it faces an even more radical challenge when we descend into the bizarre world of the very small. Quantum mechanics, the set of rules governing atoms and particles, doesn't just ignore time's direction. It actively subverts our entire classical understanding of how reality operates. In this realm, the solid, predictable universe we know dissolves into a fog of probabilities and potentialities. Particles can exist in multiple places at once, a state known as superposition, and they can become mysteriously linked across vast distances through entanglement, instantly influencing each other's states. Crucially, none of these strange phenomena show any inherent preference for the past or the future. The equations describing a particle in superposition are just as valid whether time is running forward or backward. A quantum event like the decay of a radioactive atom is fundamentally probabilistic. We can calculate the likelihood it will decay within a certain period, but the exact moment is unpredictable. And in theory, the process is reversible. The mathematics does not prohibit a scattered wave of probability from collapsing back into a single, whole particle. This complete time symmetry at the quantum level deepens the mystery of why our large-scale world feels so irrevocably one way. So how do we bridge this gap? How does the fuzzy, reversible world of quantum possibilities give rise to the definite, irreversible world of shattered glasses and fading memories? The key may lie in a process known as quantum decoherence. Imagine a single, isolated photon existing in a superposition, simultaneously behaving like a wave and a particle. This fragile state can persist, but now imagine that photon is part of our everyday world. It doesn't stay isolated for long. It immediately begins to interact with its environment, bouncing off air molecules, being measured by instruments, or simply being observed. Each of these countless interactions effectively leaks information about the photon's state into the wider world. This process destroys the delicate coherence of the superposition, forcing the system to settle into one definite outcome. It's this relentless interaction with the environment that makes quantum events appear irreversible. Once the information is out there, scattered into the environment through trillions of interactions, gathering it all back together to reverse the process becomes a practical impossibility. Decoherence is the mechanism that transforms and into or, turning myriad quantum possibilities into the single, concrete classical reality we perceive. This leads some physicists like Carlo Rovelli to a startling conclusion. Time itself may not be a fundamental ingredient of the universe. Instead, it could be an emergent property, a consequence of our limited perspective. Rovelli's relational interpretation of quantum mechanics suggests that time is not a universal backdrop against which events unfold, but rather something that only exists in relation to the interactions between quantum systems. There is no single master clock for the cosmos. An event only has a time in relation to another event, the state of one system compared to the state of another. In this view, what we experience as the flow of time is really just our perception of countless quantum interactions and the increase in correlations between systems as decoherence occurs. We are not watching a cosmic movie projected on the screen of time. We are participants in a vast, interconnected network of relationships, and our sense of temporal sequence is a story we generate from this complex web of interactions. From this perspective, time begins to look less like a river and more like a useful fiction, an approximation that works incredibly well for describing the world at our human scale, but which completely breaks down when we push our inquiries to the extremes. It is a narrative tool our brains use to make sense of change and correlation. The solidity of time wavers, suggesting it is not a fundamental layer of reality, but a construct that emerges from something deeper and more mysterious. This doesn't make time any less real to our experience, of course. The urgency of a deadline or the nostalgia of an old song remains powerfully potent. But it does force us to consider that our most intimate experience of reality might be a kind of illusion, a user interface our consciousness employs to navigate a world that is, at its heart, timeless. If the very fabric of time is an emergent property rather than a fundamental one, a construct born from quantum interactions and a specific cosmic starting point, then we must confront one of the most radical and mind-bending implications of Einstein's theory of relativity, the block universe. This model proposes a reality so foreign to our daily experience that it can feel almost impossible to grasp. It suggests that the past, present, and future are not sequential events but exist simultaneously and eternally. In this view, the entire history and future of the cosmos are laid out together in a single, vast, four-dimensional structure. Your birth, your reading of this sentence, and every moment yet to come are all equally real, fixed points in this grand cosmic architecture. Time in this model does not pass, it simply is. We are not moving through time, we are, in a very real sense, extended through it, much like an object is extended through the three dimensions of space. To wrap our minds around this, a powerful analogy is to think of a movie on a DVD. The entire film, from the opening credits to the final scene, is physically present on the disc all at once. Every frame, every line of dialogue, every moment of joy and sorrow exists in a complete and static state. This is the block universe. Our conscious experience, however, is like the laser of a DVD player, illuminating just a single frame at a time. It moves sequentially from one scene to the next, creating the illusion of a narrative unfolding, of cause leading to effect, of a story with a beginning, middle, and end. But the entire story is already there. The laser doesn't change the movie, it merely reveals it piece by piece. In the same way, our consciousness might not be moving through time, but simply tracing a path along a timeline that is already and always fully constructed. This isn't just philosophical speculation, it's a direct consequence of Einstein's groundbreaking work. His theory of relativity shattered the Newtonian idea of a single, universal clock ticking away for everyone. Instead, he revealed that time is relative. The rate at which time passes depends on your speed and your proximity to a gravitational field. An astronaut orbiting the Earth at high speed will age slightly slower than their twin on the ground. More profoundly, relativity eliminates the concept of a universal now. What appears to be the present moment for you might be the past for someone else moving at a different velocity, or the future for someone in a powerful gravitational field. There is no privileged frame of reference that can declare which events are happening at the same time for everyone in the universe. This makes the idea of a flowing, universal present untenable from a physics perspective. If you can't define a single, objective present, then it becomes very difficult to sustain the idea that only the present is real, while the past is gone and the future is not yet formed. This leads to a profound shift in perspective. We are forced to abandon the metaphor of time as a flowing river, which implies movement and change, and instead adopt the metaphor of time as a landscape. Imagine a vast four-dimensional mountain range. Within that range, every event, the formation of the Earth, the fall of the Roman Empire, your first day of school, the death of a distant star a billion years from now, is a fixed location, a specific set of coordinates in space-time. From this God's eye view, the entire topography is complete and unchanging. Our journey through life is not one of creating this landscape, but of exploring a single, predetermined path through it. The feeling of time's flow, of the future becoming the present and the present receding into the past, is not a feature of the universe itself, but a feature of our perception. It is the narrative our conscious mind projects onto this static structure to make sense of our existence. If the block universe is an accurate description of reality, then the one-way nature of time is indeed the ultimate illusion. The arrow of time is not a property of the cosmos, but a property of us, the observers. Our conscious experience, constrained by the way our brains process information and create a coherent story from a sequence of moments, generates the feeling of passage. This doesn't make our experience any less vivid or meaningful, but it does suggest that free will and destiny might be locked in a far more complex dance than we ever imagined. We are both the authors and the readers of a story that has already been written, living out a narrative that is, from a higher dimensional perspective, already complete. This perspective doesn't diminish the mystery of time. It deepens it, transforming it from a question of physics into a profound puzzle about the nature of consciousness and our place in an eternal, unchanging reality. So if the block universe is correct and all of time exists at once, we are left with the most puzzling question of all. Why does it feel like something is happening? Why do we have this powerful, undeniable sensation of a present moment that is continuously updating, of a past that recedes into memory and a future that approaches? This subjective river of experience, which philosophers call the phenomenology of time, is the final and most intimate piece of the illusion. It suggests that the arrow of time might not just be a statistical or cosmological artifact, but a deeply biological and psychological construct woven into the very fabric of our consciousness. Our brains are not passive recorders of a temporal sequence. They are active editors and interpreters, constantly stitching together a coherent narrative from a chaotic influx of sensory data. Think about the simple act of hearing a sentence. The sound waves hitting your eardrum are a continuous stream, yet you perceive distinct words and phrases. Your brain takes this raw data, holds it in a temporary buffer for a few seconds, and then processes it into a meaningful sequence. This process creates the illusion of a smooth, flowing present. It's not that we live in an instant, we live in a psychologically constructed, specious present, a window of about 2 to 3 seconds that we perceive as now. This is the fundamental unit of our temporal experience, and our consciousness glides from one to the next, creating the seamless river of time. The malleability of this experience proves that it's a construction. During a life-threatening event like a car accident, people often report that time seemed to slow down to a crawl. This isn't because the world actually decelerated. It's because our brain, flooded with adrenaline, goes into a state of hyper-alertness. It starts gathering and processing sensory information at a much higher rate, creating a denser memory of the event. When we look back on that dense cluster of memories, the event feels like it took much longer than it actually did. Conversely, when we are bored or performing a repetitive task, time seems to drag because our brain isn't forming many new or distinct memories. And when we are fully engaged and happy, time appears to fly by because our brain is efficiently processing familiar and enjoyable patterns, creating fewer unique memory markers. Our sense of time's passage is directly tied to the amount and novelty of information our brains are processing. This brings us to the work of the French philosopher Henri Bergson, who made a crucial distinction between scientific time and lived time. He argued that physicists measure time as a series of discrete, identical points on a clock, a quantitative, spatialized version of time he called duration. But this, he insisted, is an abstraction. The time we actually live is la durée, a qualitative, continuous flow of experience that is irreducible to measurement. It's the difference between looking at a musical score, which shows all the notes statically on the page, and actually listening to the melody unfold. The melody cannot be understood by analyzing its individual notes. Its essence is in its progression and flow. For Bergson, this lived duration is the fundamental reality of time, and it is inextricably linked to consciousness itself. The flow isn't happening out there in the world, it is happening in here as an integral part of our conscious experience. This perspective offers a radical solution to the physics puzzle. The reason the fundamental laws don't contain an arrow of time might be because the flow isn't a property of the external, physical world at all. Physics describes the world of objects and events, the block universe, the DVD itself. But the feeling of time passing, the movement of the laser reading the disk, is a property of the observer. It is a feature of how complex information processing systems like our brains interact with that static world. We are not detecting a flow that exists independently. We are generating that flow as a mode of perception. The arrow of time, then, is not a puzzle for physics to solve, but a puzzle for neuroscience and psychology. The question shifts from, why does the universe have a temporal arrow, to, why did consciousness evolve to perceive a timeless universe in this particular, sequential way? The answer likely lies in survival. An organism that perceives a static, unchanging world would be unable to navigate cause and effect, to learn from the past, or to anticipate the future. The illusion of temporal flow is an incredibly useful user interface for reality. It allows us to track patterns, assign causality, and plan for outcomes. It turns the vast, simultaneous block universe into a manageable, linear story where we are the protagonists. this doesn't make our experience any less real or profound. The joy of anticipation, the pain of loss, the urgency of a deadline, these feelings are the very substance of our lives. But understanding that this flow might be a brilliant cognitive adaptation allows us to hold two truths in our minds at once: that from the perspective of the cosmos, all of time may be eternally present, but from our perspective, embedded within it, the river flows on, carrying us with it, and that journey is what makes us human. This journey into the nature of time, from our psychological perception to the static block universe, brings us to the very edge of modern physics. To go further, to truly ask if time is fundamental at all, we must venture into the most ambitious and speculative realms of theoretical physics, the quest for a theory of quantum gravity. This is the monumental effort to unify the two great pillars of 20th century science, the probabilistic, particle-based world of quantum mechanics with the smooth, geometric curvature of Einstein's general relativity. It is here, in these attempts to describe the fabric of spacetime itself at the smallest possible scales, that the concept of time faces its most radical challenge. In many of these frameworks, time does not just lose its arrow, it ceases to be a fundamental ingredient altogether. Consider the scale at which this unification must occur, the Planck scale. This is an almost unimaginably tiny domain where distances are measured in units of 10 to the negative 35 meters and time intervals are around 10 to the negative 43 seconds. At this scale, the smooth, continuous spacetime of general relativity is expected to break down, becoming a seething, turbulent foam of quantum fluctuations. In this primordial froth, the very notions of before and after may become meaningless. There may be no well-defined sequence of events, no clear timeline to follow. The orderly progression we experience dissolves into a disordered, probabilistic jumble where causality itself has no foundation. In such a realm, the idea of a one-way flow is not just irrelevant, it's inapplicable. Time as a dimension might simply not exist down there in the basement of reality. This is the core idea behind many quantum gravity approaches, that time is not fundamental but emergent. It is not a primary building block of the universe but a secondary, large-scale effect, a collective property that arises from the interactions of more basic, timeless entities. A useful, though imperfect, analogy is to think of temperature. We feel temperature as a real, tangible property, but it isn't a fundamental property of the molecules in the air. A single air molecule doesn't have a temperature, it only has kinetic energy, a speed. Temperature is an emergent, statistical property that only makes sense when you have a vast ensemble of molecules jiggling around. Their average kinetic energy is what we perceive and measure as heat. In a similar way, some physicists propose that time is what emerges when we have a vast network of fundamental, timeless quantum events interacting with each other. Our smooth experience of temporal flow is a kind of average, a statistical illusion that only has meaning at our macroscopic level, much like the smoothness of a liquid emerges from the chaotic motion of its atoms. Different theories of quantum gravity tackle this emergence in fascinating ways. Loop quantum gravity, for instance, proposes that space itself is not continuous but is woven from tiny, finite loops, a fabric of discrete threads. In this picture, spacetime is literally quantized, and just as a digital photograph appears smooth and continuous from a distance but reveals its pixelated nature when you zoom in, our smooth experience of time may be a coarse-grained approximation of a reality built from discrete, timeless quanta of space. The flow of time could be analogous to the flipping of pixels on a screen, creating the illusion of motion from a series of static frames. String theory, another leading candidate, suggests that the fundamental constituents of reality are not point-like particles but incredibly tiny, vibrating strings. The properties of these strings, including their vibrational modes, determine everything we observe, from particles to forces. In some formulations of string theory, time emerges from the interactions of these strings within a higher dimensional reality. The direction of time could be related to a specific kind of symmetry breaking, or to the expansion of our particular three-dimensional universe within a larger, timeless multiverse. The arrow of time, from this perspective, might be a local phenomenon, a feature of our specific cosmic bubble rather than a law of the entire meta-universe. These theories are, for now, highly mathematical and beyond direct experimental verification, but their profound implication is clear. They point toward a truly timeless underlying reality. If time is emergent, then the one-way flow we experience is the ultimate approximation, a simplification that works incredibly well for organizing our world, but which completely fails when we try to describe the universe at its most fundamental level. The deep structure of reality might be a static, unchanging mathematical relation, a vast, complex equation where every part is simultaneously present. In this view, the Big Bang wasn't an event in time. It was the event that gave rise to time itself, the moment when this emergent property first crystallized out of a timeless quantum state. We are not living in a universe with a history. We are living inside a history, a story that is being read, not written, with the feeling of passage being the most compelling special effect of all. This is the final and most radical deconstruction of time, suggesting that our entire lived experience is a magnificent and necessary illusion played out on a stage where the very concept of when is merely a prop. But if these mind-bending theories suggest time is an emergent, illusory property, how do we move from philosophical speculation to hard, empirical evidence? How do we actually test the fundamental nature of time in a laboratory? This is where the rubber meets the road, where physicists design ingenious experiments to probe the universe's deepest secrets, trying to catch time in the act of revealing its true character. The quest is to find a violation, a tiny crack in the facade of time reversal symmetry that would prove the laws of physics are not quite as indifferent to time's direction as they appear. For decades, this search has focused on the subatomic world. Scientists meticulously study the behavior of exotic particles, looking for any process that is not perfectly symmetric when imagined in reverse. A prime candidate has been the decay of subatomic particles called kaons and their even more exotic cousins, B-mesons. The way these particles transform into other forms is governed by the weak nuclear force, which is already known to violate other symmetries like parity, which is the equivalence of left-handed and right-handed systems. The hope is that it might also violate what's known as time reversal invariance, or T-symmetry for short. If such a violation were found, it would be monumental. It would mean that at the most fundamental level, the universe's rulebook does, in fact, contain a tiny but significant arrow, a built-in preference for one direction of time over the other. This would suggest that time's flow is not just a statistical illusion, but is somehow encoded in the bedrock of physical law. While hints of such violations have been detected, the results are not yet conclusive enough to rewrite the textbooks, keeping physicists on a thrilling hunt. The quantum realm offers another, even more radical, experimental playground. Researchers are now using advanced quantum computers and other controlled systems to simulate scenarios where the arrow of time seems to run backward. In one stunning experiment, scientists at the Australian National University studied the behavior of a cloud of atoms cooled to near absolute zero. They used a precisely tuned laser beam to act as a roadblock, corralling the atoms into an ordered pattern, a low entropy state. When they released this laser corral, they watched as the atoms did what the second law of thermodynamics predicts. They spread out into a more disordered, high-entropy state. But then, by applying a specific magnetic field, they were able to essentially reverse the quantum waves of these atoms. It wasn't that they painstakingly guided each atom back to its starting point. Instead, they manipulated the quantum state of the entire system, causing it to retrace its steps. From a certain perspective, it was as if time itself was running in reverse for these particles, with disorder spontaneously reverting to order. This doesn't violate the second law on a grand scale. It took immense external effort and control to achieve, but it demonstrates that the quantum laws governing the particles are truly time-symmetric. The irreversibility we see emerges only when we lose our ability to control every single degree of freedom in a system. Perhaps the most profound challenge to our classical intuition comes from experiments investigating the very nature of cause and effect. In our everyday world, cause always comes before its effect. You throw a rock, cause, and then the window breaks, effect. This sequence is the very foundation of reality as we know it. But in the quantum world, this tidy relationship begins to fray at the edges. Experiments in quantum optics have demonstrated a phenomenon called delayed choice, where a decision made in the present appears to influence the past behavior of a particle. In one famous setup, a single photon is presented with a choice: to behave like a particle and take one path, or to behave like a wave and take two paths simultaneously. Astonishingly, the experimenter's choice to measure which path it took after the photon has already made its journey seems to determine how it behaved before the measurement was made. It's as if the effect, the measurement, reaches backwards in time to influence the cause, the photon's original decision. This doesn't mean we can send messages to the past or change history, but it fundamentally challenges our classical notion of a linear, objective timeline of events. It suggests that at the quantum level, the concepts of before and after are not as rigidly defined. The universe seems to wait until the last possible moment, until a system is finally observed or interacts with its environment, to decide on a definitive history. These quantum correlations hint at a reality where the past is not fixed until it is interrogated by the present, an idea that turns causality from a chain of events into a tangled web of possibilities. This is the practical, empirical front line in the war on time. It's no longer just a debate for philosophers and theorists huddled over blackboards. It's a field of active experimentation, where physicists are developing the tools to potentially unmask time's flow as the most convincing and pervasive perceptual trick the universe has ever played on us. Yet this statistical view of entropy, while powerful, opens up a bizarre and profound paradox that forces us to question the very foundations of our reality. If the arrow of time is merely a matter of overwhelming probability, not an unbreakable law, then the door is cracked open for truly strange possibilities. In a universe that is infinite in either space or time, or one that persists for an unimaginable eternity, even the most astronomically improbable events are not just possible, they are inevitable. Given enough time and enough space, every possible combination of particles will eventually occur by random chance. This includes the spontaneous formation of a fully functioning, conscious brain, complete with a set of fabricated memories emerging from the chaos of a random quantum fluctuation. Physicists call such a hypothetical entity a Boltzmann brain. The implication is as unsettling as it is fascinating. If such self-aware fluctuations are possible, how could we ever know that we are not one? How can we be certain that our memories of a childhood, our sense of a continuous past, and our entire understanding of a universe with a history are real? and not just a detailed, momentary illusion generated by a freak accident in the void. This isn't merely a science fiction trope. It's a serious philosophical problem that emerges directly from taking the statistical nature of entropy to its logical extreme. It suggests that in the grand, cold calculus of probability, ordered, conscious observers like us should be vastly outnumbered by these random, disembodied fluctuations. The fact that we perceive a coherent and continuous universe around us, then, becomes a deep mystery. This paradox forces physicists to look for a more fundamental explanation for our low entropy beginning, something that makes our ordered existence not a wildly improbable fluke, but a necessary outcome of the universe's laws. This leads us to a modern refinement of these ideas, often called the fluctuations theory. While the overall entropy of our entire observable universe has been increasing since the Big Bang, we can actually observe temporary and localized decreases in entropy in small, isolated systems all the time. Imagine a perfectly still room. The air molecules are in a state of relatively high entropy, bouncing around in a chaotic, disordered way. But by pure chance, there will be brief instants where a group of molecules in one corner of the room all happen to move in the same direction at the same time, creating a tiny, organized gust of wind. For a fleeting moment, entropy in that corner has decreased. Order has emerged from disorder spontaneously, before the greater trend reasserts itself and the gust dissipates back into random motion. Now scale this idea up, way up, over trillions upon trillions of years, in a corner of a universe that has otherwise reached a state of maximum disorder, a featureless heat death, where energy is evenly spread out and nothing ever happens. A fluctuation vast enough to create an entire new universe could theoretically occur. This is the basis of some cosmological models that suggest our own Big Bang might not have been a unique starting point, but merely one particularly large and energetic fluctuation in a much older, eternal, and mostly dead meta-universe. In this dizzying picture, the arrow of time is not just statistical, it's cyclical and local. Our entire cosmic history, from the Big Bang to the eventual heat death, could be just one bubble of order in an infinite sea of chaos, with its own internal arrow of time that is completely separate from the timeless stillness outside of it. This perspective completely shatters any remaining notion of time's arrow as an absolute, universal constant. It becomes a relative property, entirely dependent on context and scale. For us, living inside this specific, low-entropy bubble, the flow from past to future feels absolute and undeniable. But from a God's-eye view outside our cosmic horizon, our entire timeline might be just a brief, insignificant flicker of structure. The flow of time is not an illusion in the sense that it isn't real to us. It is profoundly real within our reference frame. But its solidity is an illusion in the sense that it is not a fundamental feature of the cosmos. It is a contingent, emergent property of our particular place within it, a story that is true here but may be completely irrelevant elsewhere. By embracing these ideas, we are forced to accept that the relentless, one-way current we are all floating on is not the river itself, but merely the appearance of a current from our particular raft. So where does this leave our cosmic story? If the arrow of time is a local phenomenon born from a specific low-entropy beginning, then the ultimate fate of our universe becomes crucial to understanding time's true nature. Cosmology doesn't just tell us where we came from, it offers a startling prophecy for where we're headed, and that destination paints a haunting picture for the future of time itself. The most widely accepted forecast, based on our current understanding of dark energy and the universe's expansion, is known as the heat death. Imagine a cosmos that continues to expand forever. Galaxies drift apart until each is an isolated island in a vast, ever-growing void. Within those galaxies, stars slowly burn through their fuel. One by one, they flicker and die, their fires extinguished. Eventually, even the supermassive black holes, the last bastions of order, will evaporate away through a process known as Hawking radiation. What remains is a universe that has reached a state of maximum entropy, a thin, cold, ultra-diffuse soup of particles and radiation, evenly distributed across an infinite emptiness. In this final state, there are no temperature differences, no energy gradients, no structures of any kind. Nothing ever happens. There is no change. And if there is no change, can we truly say that time exists? Time, after all, is the metric of change. We measure it by the oscillation of atoms, the orbit of planets, the burning of stars. Without any processes, without any events to mark its passage, time loses all meaning. It becomes a dimension without a clock, a coordinate without consequence. The universe would enter a state of eternal, static equilibrium. From our perspective, hurtling forward on the arrow of time, this seems like a bleak and final end. But from the perspective of the underlying physics, it might simply be the universe settling into its most natural, probable, and timeless state. The heat death isn't an explosion or a collapse. It's the universe finally winding down, its great thermodynamic engine sputtering to a halt, and with it, the very concept of when fading into irrelevance. But what if our universe's story doesn't end with this silent, frozen whimper? Some cosmological models propose a far more dramatic and cyclical fate, one that could fundamentally reset the arrow of time itself. This is the idea of a cyclic universe. In one compelling version, our current phase of expansion might eventually be reversed by the collective gravitational pull of all matter and energy, leading to a big crunch. The universe would collapse back in on itself, heating up and compressing to an incredible density. In some speculative theories, this collapse might not be the end. Instead of vanishing into a singularity, the universe could bounce. The incredible energies and pressures of the crunch could trigger a new Big Bang, birthing a new universe from the ashes of the old. This cycle of expansion, contraction, and rebirth could, in theory, repeat forever. Now, here's the profound twist for time's arrow. If entropy were somehow reset during this bounce, if the new universe began in a state of low entropy all over again, then the arrow of time would reverse with each new cycle. Beings born in the next cycle would perceive the crunch as their Big Bang. Their future would be what we call our past. Their past would be our future. The flow of time would be completely inverted. This isn't just a reversal of clocks, it's a fundamental flipping of causality and memory. Of course, the major hurdle for this idea is the second law of thermodynamics. How could entropy, which only increases, possibly reset? It's a colossal problem, but some theorists, like the renowned Roger Penrose, have proposed an ingenious way around it. His model, called conformal cyclic cosmology, suggests that in the far, far future, at the end of time during the heat death, the universe becomes so vast and empty that the concept of scale loses all meaning. Distances become irrelevant. In this strange, conformally invariant state, a universe of maximum entropy becomes mathematically identical to a universe of minimum entropy, a singularity. This allows for a seamless transition, a sort of cosmic recycling where the endless future of one universe becomes the hot, dense, low entropy beginning of the next. In this breathtaking vision, our Big Bang was merely one event in an infinite chain of eons, each with its own arrow of time, its own history, and its own future, all eternally linked. These models, from the silent heat death to the dramatic cosmic cycles, force a radical realization. Time's flow is not an independent, absolute entity that exists outside the universe. It is inextricably tied to the universe's content and its dynamics. Time needs things to happen to it. It requires energy gradients, quantum events, and the relentless increase of entropy to give it direction and meaning. Without the unfolding drama of the cosmos, the birth of stars, the formation of planets, the intricate dance of particles, time is just an empty stage. It is an emergent property, a side effect of the universe being in a state of dynamic change. And if the universe ever ceases to change, or if it resets and begins anew, time as we know it ceases or flips accordingly. Our intimate, unwavering experience of a one-way flow is not a universal constant. It is a temporary, local condition, a fleeting chapter in a story that may be, on the grandest scales, utterly timeless. This radical rethinking of time doesn't just rewrite physics textbooks. It strikes at the very core of our human experience, forcing us to confront some of the most profound philosophical questions imaginable. If the block universe is real and all of time exists simultaneously, then the entire narrative of our lives, the struggle, the growth, the sense of becoming, is called into question. It suggests that the person you are at this very moment, the child you once were, and the elderly person you may become are all equally real, fixed points in a vast, unchanging structure. This immediately plunges us into the ancient and heated debate between determinism and free will. If the future is already written and exists just as solidly as the past, in what meaningful sense can we be said to be making choices? Your decision to watch this video, for instance, wouldn't be a spontaneous act of free agency emerging from the present moment, but a predetermined event that was always destined to occur at these specific coordinates in spacetime. This is a classic deterministic view, where the universe is a complex clockwork mechanism, and our feeling of choice is merely the illusion of a cog that doesn't understand the clock. Yet, many philosophers and scientists argue that this is a false dichotomy. They propose that free will and determinism might be compatible in a way that preserves our sense of agency. This view, known as compatibilism, suggests that even if the universe is deterministic at a fundamental level, our choices are still free if they arise from our own desires, beliefs, and character without external coercion. In the block universe model, your decision to watch this video is indeed a fixed point, but it is a point that is authentically you. It emerges from your unique neural architecture, your history, and your personality. The choice is determined, but it is determined by who you are. This perspective doesn't erase responsibility. It grounds it more deeply in the fabric of our identity. The challenge, then, is to reconcile this fixed existence with our overwhelming inner experience of deliberation and possibility, a tension that remains one of philosophy's greatest puzzles. This crisis of agency is intimately tied to a crisis of identity. The common-sense view of the self is a narrative one. We are the main character in an ongoing story that stretches from birth to death. Our identity is the thread of memory that connects these experiences, giving us a sense of a continuous, evolving self. But if all moments exist at once, this narrative collapses. The self is no longer a story unfolding in time, but a collection of disparate time slices or stages, each one a separate entity frozen in the eternal block. The you reading this sentence is a distinct entity from the you that will finish it, and both are separate from the you that was 7 years old. They are linked by similarity and causal connection, but they do not share a single, flowing consciousness. This stage theory of personal identity, proposed by philosophers like David Lewis, suggests that what we call the self is a series of momentary beings, each one psychologically connected to the others, creating the powerful but mistaken impression of a single, enduring person. This can feel alienating, as if our most fundamental sense of being is a kind of pleasant fiction we tell ourselves to navigate a static reality. The German philosopher Immanuel Kant offered a powerful way to navigate this unsettling terrain over 2 centuries ago. He argued that time and space are not objective features of the external world, but fundamental frameworks of the human mind itself. He called these frameworks intuitions. We cannot help but perceive the world through the lens of time. It is the very operating system of our consciousness, the way we organize sensory data into a coherent experience. For Kant, asking what the world is like outside of time is a meaningless question because we have no way to access it. The block universe, in this view, might be the thing in itself, the reality that exists independently of our perception, but we are forever barred from experiencing it directly. We are doomed, or perhaps blessed, to experience reality only as a temporal sequence. This means the debate isn't about whether time is real to us, it undeniably is. The debate is about whether that reality is a property of the universe or a property of the mind that observes it. Kant firmly places the arrow of time within us, making our conscious experience the source of time's flow, not a passive recorder of an external current. This has staggering implications for morality and meaning. Our entire ethical framework is built upon temporality. We hold people responsible for past actions, we make promises about the future, and we strive to create a better world for generations to come. This is a teleological view, one oriented toward goals, purposes, and ends. But if the future is already fixed and the past is not truly gone, what happens to this forward-looking drive? Does the concept of moral progress become an illusion? Some thinkers suggest that a timeless perspective might actually deepen our sense of ethics, shifting the focus from achieving future outcomes to appreciating the intrinsic value of each moment. If all of existence is eternally present, then every act of kindness, every moment of joy, and every instance of suffering has a permanent, unchanging reality. This could instill a profound sense of responsibility for the quality of each moment, as it is not a fleeting event that disappears into the past but an eternal fact of the cosmos. Meaning is no longer found in progress toward a future goal, but in the quality and depth of our participation in the eternal now. This invites a radical shift in how we might choose to live. If time is indeed a mental construct, then our chronic anxiety about the future and our lingering regrets about the past are misunderstandings of our true situation. We are not hurtling toward an uncertain destiny. We are eternally present at every point of our story. This perspective is echoed in many contemplative traditions, from Buddhist mindfulness to the Christian concept of the eternal present in God. The practical invitation is to loosen our grip on the temporal narrative and sink more fully into the present moment, the only point where we can actually experience reality. This doesn't mean abandoning planning or reflection, but rather engaging in them without the underlying belief that our entire existence is defined by a linear trajectory. It means recognizing that while we are compelled to live our lives in time, we might find our deepest meaning by connecting to a dimension of experience that feels, however faintly, timeless. Ultimately, unraveling the illusion of time's arrow does more than transform physics. It asks us to reimagine what it means to be human, challenging us to find our purpose not in the flow of time, but in the depth and quality of the moments that constitute our eternal being. But if the universe is truly a static block and time is an illusion, then we must confront one of the most thrilling and mind-bending consequences of this idea, the theoretical possibility of time travel. This isn't just the stuff of science fiction. It emerges directly from the equations of our most successful theory of gravity, Einstein's general relativity. The theory describes gravity not as a force, but as the warping of spacetime by mass and energy. And when spacetime is warped in extreme ways, it can create structures that seemingly bend the timeline back on itself. These are known as closed time-like curves. A closed time-like curve is essentially a path through the cosmos that, if you were to follow it, would bring you back to your own past. It's a loop in the fabric of spacetime itself. The most famous hypothetical example is a wormhole, a tunnel or shortcut connecting two distant points in spacetime. If one end of a wormhole were accelerated to a significant fraction of the speed of light and then brought back, time dilation effects from relativity would cause that end to be much younger than the stationary end. If you then stepped into the stationary end, you would exit the accelerated end in your own past. You wouldn't be traveling faster than light. You'd be taking a cosmic shortcut made possible by the flexible geometry of spacetime. Other theoretical constructs, like an infinitely long, rotating cylinder or the region around a ring of spinning black holes, could also, in theory, create these reality-bending paths. Their mere possibility within the framework of physics suggests that the universe's rulebook does not explicitly forbid visiting the past. It just makes it incredibly difficult from an engineering perspective. This immediately throws us into the deep end of logical paradoxes, the most famous of which is the grandfather paradox. Imagine you built a time machine and traveled back to a time before your grandfather had children. If you were to prevent him from meeting your grandmother, then your parent would never be born, and consequently, you would never be born. But if you were never born, you could never have traveled back in time to interfere with the event in the first place. So, your grandfather would meet your grandmother, you would be born, and you would travel back in time, creating an unresolvable loop of cause and effect that seems to violate the most basic logic of our universe. This paradox is the ultimate weapon against the idea of a mutable past, suggesting that if time travel were possible, the very fabric of reality would unravel into logical nonsense. So how does physics grapple with this? One compelling resolution is the principle of self-consistency, championed by physicists like Igor Novikov. This idea posits that any actions taken by a time traveler were always part of history. The timeline is a single, immutable block, and it is consistent. You cannot change the past because you were always part of it. In the case of the grandfather paradox, this means that any attempt you make to alter events would inevitably fail. Your gun would jam, you would miss your shot, or you would have a sudden change of heart. The events would unfold precisely as they always did, with your presence in the past being a hidden, integral part of the story that led to your own birth. Your journey back wasn't an interruption of the timeline. It was always a feature of it. This view is perfectly compatible with the block universe model, where the past is just as fixed and unchangeable as a distant star. Another, even more radical solution comes from the multiverse interpretation, often linked to the ideas of Hugh Everett in quantum mechanics. In this scenario, time travel doesn't mean going back into your own past. Instead, it would involve shifting to a different, parallel universe that is nearly identical to your own past up to the moment you arrive. In this new branch of reality, your actions are free from paradox. You could prevent that version of your grandfather from having children, and it would have no effect on the original timeline you came from. You would simply have created a new, alternative universe in which you never exist. This doesn't resolve the paradox so much as sidestep it entirely by suggesting that every possible outcome happens in its own separate reality. The one-way flow of time is preserved within each individual universe, but the multiverse as a whole becomes a complex, branching tree of possibilities where the very idea of a singular timeline becomes obsolete. What makes these thought experiments so much more than just fun puzzles is that they serve as a powerful stress test for our physical theories. By entertaining the possibility of closed time-like curves and grappling with their paradoxes, physicists are indirectly probing the deepest nature of causality and time itself. If general relativity allows for solutions that include time travel, but we never observe it in the real world, then there must be a deeper principle at work that prevents it, a kind of cosmic censorship. Some theorists propose that quantum effects, which become incredibly important in the extreme conditions required for time travel, might always conspire to prevent these paradoxes from occurring, perhaps by making the required exotic matter unstable or by causing wormholes to collapse the instant they might be used for time travel. This suggests that the linear, one-way flow of time we experience might be a protected, emergent property, a feature that is enforced by the laws of physics to maintain a stable, logical universe, even if those same laws don't explicitly demand it at a fundamental level. Therefore, the very act of taking time travel seriously forces us to a profound conclusion. The arrow of time might be flexible, but it is also resilient. It might not be written into the most basic equations, but it appears to be enforced by the universe to preserve consistency and causality on macroscopic scales. This exciting frontier shows that our classical intuition of a rigid, linear timeline is indeed an illusion, but it's an illusion that the universe goes to great lengths to uphold. By pushing the boundaries of what reality might allow, we aren't just dreaming of visiting the dinosaurs. We are conducting a crucial experiment on the nature of reality itself, testing whether the flow of time is a fundamental current or a local eddy in a much stranger and more complex cosmic ocean. This intricate dance between entropy and probability leads us to a fascinating parallel universe of ideas, the world of information theory. If entropy is a measure of disorder, then information is, in a very real sense, its opposite, a measure of order, structure, and surprise. Think about a perfectly blank sheet of paper. It contains very little information. Its state is predictable and uniform. Now, imagine that same paper with a complex poem written on it. The specific arrangement of ink, the carefully chosen words, represent a highly improbable and therefore highly informative state. This is the profound insight of information theory, pioneered by Claude Shannon. Information is deeply linked to uncertainty and probability. The more surprising or unlikely a message is, the more information it carries. And just like entropy, the information content of a closed system has a tendency to increase over time, not because new information is being created from nothing, but because randomness and noise corrupt and scramble existing information, making it more disordered and unpredictable. A whispered secret passed through a long chain of people becomes distorted, gaining erroneous details and losing its original meaning. Its information becomes more chaotic, mirroring the increase in thermodynamic entropy. This connection isn't just a loose analogy, it's a hard physical principle with serious consequences. This is where Landauer's principle enters the stage, forging an unbreakable link between the abstract world of information and the concrete reality of physics. Formulated by Rolf Landauer in the 1960s, this principle states a deceptively simple but profound truth. Erasing information is not a free lunch. Any time a computer or any system resets a bit of information from a 1 to a 0, or vice versa, it must pay a minimum energy cost. That energy isn't lost, it is dissipated as heat, increasing the entropy of the surrounding environment. Why is this? Because to erase a bit, to force it into a known state, you have to get rid of the uncertainty about its previous value. That act of forgetting, of reducing the number of possible states the system could be in, is an inherently irreversible process that inevitably generates heat. Your laptop gets warm not just from electrical resistance, but from the very act of computation itself every time it clears a memory register to make room for new data. It is literally generating entropy, a tiny puff of thermal disorder that is the direct price of forgetting. Landauer's principle gives the arrow of time a tangible, measurable footprint in the process of information handling. But what if we could build a computer that never had to forget? This isn't science fiction, it's the field of reversible computing. In a standard, irreversible computer, logic gates take inputs and produce outputs, but the original inputs are lost in the process. This is why your computer consumes power and heats up. A reversible computer, however, is designed so that every operation can be run backwards. No information is ever erased, it is only transformed and conserved. If you know the output of a reversible logic gate, you can perfectly reconstruct what the input must have been. Because no information is destroyed, Landauer's principle suggests that such a computer could, in theory, operate with vanishingly small energy consumption and produce almost no heat. This isn't just a recipe for incredibly efficient laptops, it's a staggering conceptual breakthrough. It demonstrates that at the microscopic level of logical operations, the arrow of time, as defined by the inevitable increase of entropy, is not a mandatory feature. The fundamental act of processing information does not, by itself, require time to have a direction. Reversible computing shows that the one-way flow we associate with computation, and by extension with cause and effect, is a consequence of our practical, macroscopic need to erase and forget, not a law of physics itself. This brings us to the provocative ideas of physicists like Seth Lloyd, who pushes this concept even further. Lloyd argues that the flow of information doesn't just correlate with time's arrow, it might actually define it. In this view, what we perceive as the progression of time is really just the relentless processing and copying of information from one part of the universe to another. A photon carries information from a star to your eye. A neuron fires and transmits information in your brain. A rock records the information of its own erosion. The entire cosmos is engaged in a constant universe-scale computation. The direction from past to future is simply the direction in which information spreads and becomes correlated across different systems. We remember the past because information about past events has been copied and stored in our brains and in the environment. The future is unknown because information about it hasn't arrived yet. This is a powerful and compelling framework, but it rests on the same shaky foundation as the thermodynamic arrow. It requires an initial state where information was highly concentrated and ordered, ready to spread out and mix. And so, we arrive at the most radical implication of this interdisciplinary approach. If information can be conserved and processed reversibly, and if our experience of time's flow is just the propagation of information, then the one-way nature of time begins to look less like a fundamental law of the cosmos and more like a feature of our particular perspective. It's a feature of how we, as macroscopic beings made of trillions of atoms, necessarily interact with the world. We are local, temporary pockets of order that maintain themselves by constantly consuming energy and expelling entropy. Our very existence depends on this irreversible processing. We breathe in oxygen and exhale carbon dioxide. We eat ordered nutrients and excrete disordered waste. Our survival is a continuous fight against equilibrium, and this fight requires a clear direction of time. The universe itself, viewed from a God's eye perspective where every bit of information is forever conserved, might be utterly timeless. The flow we feel so intensely could be the experience of being a subsystem within a vast, interconnected network, constantly exchanging information and trying to make sense of our tiny corner of it. This doesn't make time any less real for us, but it suggests its grip is not absolute. It is a compelling story woven by our own biological and neurological need to create a coherent narrative from the endless, timeless dance of information. Yet this bizarre connection between entangled particles is only half the story. The real challenge to our classical worldview emerges when we combine this spooky action with the way we measure these particles, leading to experiments that seem to shatter the very foundation of cause and effect. The most mind-bending of these is the delayed choice quantum eraser experiment. Imagine a setup where a single photon is given a choice to behave like a particle or a wave. It's sent towards a device that can measure which path it takes, but here's the twist: a second entangled photon is created at the same time and sent on a much longer journey. The fate of this second photon is decided by a random number generator after the first photon has already been measured and has presumably already decided its own behavior. Astonishingly, the results show that the choice made for the second photon, in what we call the future, appears to retroactively determine whether the first photon in the past traveled as a particle or a wave. It's as if the effect reaches backwards in time to influence its own cause. This isn't just a theoretical puzzle. It's a result that has been demonstrated in laboratories, forcing physicists to confront the possibility that at the quantum level, the sequence of events we hold so dear is not a fixed timeline but a flexible web of correlations. The universe seems to postpone making a definitive decision about the past until the future interrogates it, suggesting that history is not a closed book but a story that remains unwritten until it is read. This phenomenon is what physicists call temporal non-locality. It's the idea that events are not strictly bound by a local and linear sequence in time. Just as entanglement shows that physical properties aren't confined to a specific point in space, these experiments hint that events might not be confined to a specific point in time either. The past, present, and future appear to be deeply interconnected in a way that makes our everyday notion of a flowing, one-way timeline seem like a crude approximation. This doesn't mean we can send messages to the past or change history in a macroscopic sense. The universe has clever ways of preserving overall consistency to prevent paradoxes. But it strongly implies that the solid, objective past we believe in is a kind of illusion. The timeline is not a pre-recorded film. It's more like a live, interactive performance where the final act can somehow rewrite the opening scene. In this quantum view, the universe is a single, unified whole where distinctions between before and after are not fundamental properties but emerge from our specific way of interacting with it. We are like audience members who can only see one spotlighted actor at a time, mistakenly believing their soliloquy is the entire play, unaware of the intricate, timeless connections between all the players on the stage. When we embrace this full spectrum of quantum weirdness from entanglement to delayed choice, it becomes clear that the bedrock laws of physics are already whispering that time's arrow is not an absolute dictate. The fundamental equations governing these phenomena show a complete symmetry. They work just as well whether time is running forward or backward. The relentless, one-way flow we experience is not written into these laws. Instead, it seems to be a large-scale consequence, a story that emerges from the collective behavior of countless quantum events, much like the smoothness of a liquid emerges from the chaotic jostling of its molecules. The arrow of time is a perspective, a compelling narrative that makes sense to creatures like us who are built from these particles, process information irreversibly, and are forever riding the wave of increasing entropy from the Big Bang. But under the intense scrutiny of quantum experiments, This perspective breaks down, revealing a reality that is far stranger and more interconnected than our classical intuition could ever allow. It suggests that our journey from cradle to grave is not a solitary voyage down a river of time, but a path we trace through an eternal, four-dimensional landscape where every point is equally real and every moment is forever now. So if the block universe is correct and all of time exists at once, we are left with the most puzzling question of all. Why does it feel like something is happening? Why do we have this powerful, undeniable sensation of a present moment that is continuously updating, of a past that recedes into memory and a future that approaches? This subjective river of experience, which philosophers call the Phenomenology of Time, is the final and most intimate piece of the illusion. It suggests that the arrow of time might not just be a statistical or cosmological artifact, but a deeply biological and psychological construct woven into the very fabric of our consciousness. Our brains are not passive recorders of a temporal sequence. They are active editors and interpreters, constantly stitching together a coherent narrative from a chaotic influx of sensory data. Think about the simple act of hearing a sentence. The sound waves hitting your eardrum are a continuous stream, yet you perceive distinct words and phrases. Your brain takes this raw data, holds it in a temporary buffer for a few seconds, and then processes it into a meaningful sequence. This process creates the illusion of a smooth, flowing present. It's not that we live in an instant, we live in a psychologically constructed, specious present, a window of about 2 to 3 seconds that we perceive as now. This is the fundamental unit of our temporal experience, and our consciousness glides from one to the next, creating the seamless river of time. The malleability of this experience proves that it's a construction. During a life-threatening event like a car accident, people often report that time seemed to slow down to a crawl. This isn't because the world actually decelerated. It's because our brain, flooded with adrenaline, goes into a state of hyper-alertness. It starts gathering and processing sensory information at a much higher rate, creating a denser memory of the event. When we look back on that dense cluster of memories, the event feels like it took much longer than it actually did. Conversely, when we are bored or performing a repetitive task, time seems to drag because our brain isn't forming many new or distinct memories. And when we are fully engaged and happy, time appears to fly by because our brain is efficiently processing familiar and enjoyable patterns, creating fewer unique memory markers. Our sense of time's passage is directly tied to the amount and novelty of information our brains are processing. This brings us to the work of the French philosopher Henri Bergson, who made a crucial distinction between scientific time and lived time. He argued that physicists measure time as a series of discrete, identical points on a clock, a quantitative, spatialized version of time he called duration. But this, he insisted, is an abstraction. The time we actually live is la durée, a qualitative, continuous flow of experience that is irreducible to measurement. It's the difference between looking at a musical score, which shows all the notes statically on the page, and actually listening to the melody unfold. The melody cannot be understood by analyzing its individual notes. Its essence is in its progression and flow. For Bergson, this lived duration is the fundamental reality of time, and it is inextricably linked to consciousness itself. The flow isn't happening out there in the world, it is happening in here as an integral part of our conscious experience. This perspective offers a radical solution to the physics puzzle. The reason the fundamental laws don't contain an arrow of time might be because the flow isn't a property of the external, physical world at all. Physics describes the world of objects and events, the block universe, the DVD itself. But the feeling of time passing, the movement of the laser reading the disc, is a property of the observer. It is a feature of how complex information processing systems like our brains interact with that static world. We are not detecting a flow that exists independently. We are generating that flow as a mode of perception. The arrow of time, then, is not a puzzle for physics to solve, but a puzzle for neuroscience and psychology. The question shifts from, why does the universe have a temporal arrow, to, why did consciousness evolve to perceive a timeless universe in this particular, sequential way? The answer likely lies in survival. An organism that perceives a static, unchanging world would be unable to navigate cause and effect, to learn from the past, or to anticipate the future. The illusion of temporal flow is an incredibly useful user interface for reality. It allows us to track patterns, assign causality, and plan for outcomes. It turns the vast, simultaneous block universe into a manageable, linear story where we are the protagonists. This doesn't make our experience any less real or profound. The joy of anticipation, the pain of loss, the urgency of a deadline, these feelings are the very substance of our lives. But understanding that this flow might be a brilliant cognitive adaptation allows us to hold two truths in our minds at once: that from the perspective of the cosmos, all of time may be eternally present, but from our perspective, embedded within it, the river flows on, carrying us with it, and that journey is what makes us human. While modern physics uses complex mathematics to deconstruct our linear experience of time, this radical questioning finds a profound echo in humanity's oldest wisdom traditions. Long before Einstein penned his equations or Boltzmann calculated probabilities, ancient philosophers and mystics were arriving at strikingly similar conclusions through introspection and spiritual inquiry, suggesting a deep and timeless intuition about the nature of reality. In the East, particularly within the vast tapestry of Hindu philosophy, the concept of time is not a river flowing in one direction but a wheel, eternally turning. The ancient Vedic texts describe immense cycles of creation and dissolution, known as kalpas, where the universe is breathed forth from a divine source, exists for an eon, and is then reabsorbed only to be born again. This cosmic rhythm, repeating across an infinity of time, presents a view of temporality that is cyclical, not linear, where beginnings and endings are merely relative points on an endless circle. This stands in stark contrast to the Western historical view, heavily influenced by Judeo-Christian thought, of time as a linear arrow launched from a singular creation event and hurtling toward a final day of judgment, a narrative that perfectly mirrors our one-way psychological experience. The Eastern model, however, challenges this very foundation, proposing that the arrow we feel so intensely might just be a single arc in a much grander, repeating pattern that our limited perspective cannot perceive in its entirety. Perhaps the most direct parallel to the block universe of modern physics comes from the school of Advaita Vedanta, which means non-dualistic end of knowledge. This philosophy introduces the concept of Maya, a term often simplified to illusion, but whose meaning is far more nuanced. Maya is not the idea that the world is not there. It is the understanding that the world is not what it appears to be. It is the veiling power that causes us to perceive the one, unchanging, ultimate reality, known as Brahman, as a fragmented world of separate objects, subjects, and crucially, a linear progression of time. In this view, the past, present, and future are all equally part of the illusion, a grand and convincing story projected upon the timeless, singular canvas of Brahman. Our journey from birth to death, our memories and anticipations are all contained within this dream. The goal of the spiritual seeker is to see through Maya, to awaken to the reality that the true self, the Atman, is not a character in the timeline but is identical with Brahman itself. the timeless witness for which the entire drama of time unfolds. This is a breathtakingly precise metaphysical counterpart to the four-dimensional block universe, where all events in space-time simply are, and the flow is a property of the observer's consciousness, not the observed reality. Buddhism, born from the same cultural soil, arrives at a similar destination via a different path. The Buddha's core teaching of anicca, or impermanence, states that all conditioned things are in a constant state of flux. Nothing remains the same from one moment to the next. Reality is a cascade of fleeting events. This ceaseless arising and passing away is what creates the illusion of a continuous self and a flowing time. The Buddhist doctrine of dependent origination further explains that all phenomena arise based on a complex web of causes and conditions, not in a simple linear chain but in an interdependent network. This web-like causality resonates deeply with the quantum idea of temporal non-locality, where the clear sequence of cause and effect becomes blurred. For Buddhism, the suffering of humanity is rooted in our clinging to this impermanent stream, our belief in a solid self that persists through time. Enlightenment, therefore, involves a profound shift in perception, not just ethically, but epistemologically, where one sees directly the empty, dependently originated nature of all things and is released from the tyranny of the temporal illusion. This awakened state is often described as touching the timeless or dwelling in the eternal present, a direct experience that transcends the conventional reality of past and future. When we place these ancient insights beside the conclusions of modern cosmology and quantum mechanics, the convergence is nothing short of remarkable. The block universe, a chillingly beautiful model that emerges from the cold logic of relativistic physics, finds a passionate, experiential counterpart in the concept of Maya. The physicist's mathematical description of a static, four-dimensional spacetime continuum is the scientist's way of pointing to what the Hindu sage calls Brahman, the ultimate, unchanging reality. The psychological arrow of time, explained by neuroscience as a construct of memory and anticipation, is what the Buddhist would call the conditioned mind, perpetually grasping at a stream of moments and weaving them into a false narrative of a self. These are not merely vague similarities, they are two powerful, independent lines of human inquiry, one outward through experimentation and one inward through contemplation, arriving at the same staggering conclusion, that our universal, visceral experience of time's flow is the central and most compelling feature of our perceived reality, and yet it may be the universe's most sophisticated illusion. This dialogue between the laboratory and the lotus position enriches our exploration immensely, reminding us that the mystery of time is not just a technical problem to be solved, but a fundamental aspect of the human condition that has captivated our greatest minds for millennia. It suggests that questioning the arrow of time is a perennial inquiry, a deep-seated intuition that we are now finally empowering with the rigorous tools of scientific method, hoping to validate with data what mystics have claimed for ages. Now, to truly challenge our intuition, we must venture beyond the analogies and enter the pristine, abstract world of mathematical physics. Here, in the language of the universe, time undergoes its most radical transformation. It is stripped of all its familiar qualities, its flow, its direction, its palpable presence, and is reduced to a simple, cold variable, t. In the equations that govern reality, from Newton's laws to Einstein's field equations, time is not a river but a coordinate, a parameter in a vast, multi-dimensional geometry. It is treated with exactly the same mathematical footing as a spatial coordinate like x or y. This is the heart of the block universe, not as a philosophical idea, but as a direct consequence of how our most successful theories are formulated. The equations don't describe a world evolving in time. They describe a world where time is just another axis, and the entire history is a static, frozen shape. When a physicist writes down a solution, they are not predicting a future. They are describing the entire four-dimensional structure of a physical system, from its beginning to its end, all at once. This mathematical demotion of time reaches its most extreme and baffling conclusion in the quest for a theory of quantum gravity. The ultimate goal here is to unify the general theory of relativity, which describes gravity as the curvature of space-time, with quantum mechanics, which describes the probabilistic behavior of particles. When physicists attempt to apply the rules of quantum theory to the entire universe, a field known as quantum cosmology, they run into a profound problem. The result is the Wheeler-DeWitt equation, named after the physicists John Wheeler and Bryce DeWitt. This equation is arguably one of the most provocative in all of physics because of what it conspicuously lacks, the time variable t. It completely disappears. The equation describes the quantum state of the entire universe, but it does so in a way that is utterly static. There is no before or after in the Wheeler-DeWitt equation. It simply gives a probability for the universe to have a certain configuration, full stop. It's as if the most fundamental description of reality has no place for time at all, treating it as a mere illusion that emerges only when we look at a subset of the whole. The equation seems to suggest that the universe at its core is fundamentally timeless. So how do we recover the familiar world of change and sequence from a timeless foundation? The leading idea is that time is an emergent property, a concept that arises from more fundamental, timeless building blocks. Think of it like temperature. A single molecule doesn't have a temperature. Temperature is a property that only makes sense when you have a vast collection of molecules jostling around. Their average energy is what we measure as heat. In a similar way, time might be what physicists call an emergent phenomenon. It isn't a fundamental ingredient but a large-scale consequence, a story that makes sense for complex systems like us who are embedded within the universe. The flow of time could be a result of the universe's increasing entropy, or it could emerge from the quantum correlations between different parts of the system. From this perspective, the t in our everyday equations isn't pointing to a deep cosmic clock. It's a convenient parameter we use to track our position within this emergent narrative, a useful handle for creatures of our scale to make sense of a reality that is, at its foundation, changeless. This mathematical view forces a complete inversion of how we normally think. We are accustomed to seeing objects changing in time, a planet orbiting, a leaf falling. But if time is emergent, then this is backwards. Change does not happen within time. Change is what creates the illusion of time. The universe is a vast network of interrelated events. Our conscious awareness, with its limited perspective, scans across this network, and each new correlation or interaction is interpreted by our brain as a new now. The sequence of these nows is what we experience as the flow of time, but the mathematics implies that this sequence is not a primary feature of the cosmos. It is a reading, not a writing, a viewing, not a doing. The parameter t is not a director of the cosmic play, but simply a page number we assign for our own convenience, while the entire script already exists complete and entire in the library of eternity. This construction of time isn't just a philosophical idea. It's a physical process happening inside our heads, and neuroscience is now revealing the exact mechanisms behind it. Deep within the brain, a network of regions works in concert to create our seamless experience of temporal flow. The prefrontal cortex, vital for planning and working memory, helps us maintain a sequence of events. The parietal lobe assists in processing the duration of those events, while the hippocampus is crucial for stamping those experiences with a timestamp, filing them away as long-term memories with a chronological order. But perhaps the most fascinating player is a small, densely packed cluster of neurons in the basal ganglia called the striatum. This area acts like a central pacemaker or a metronome, firing rhythmic signals that help the brain measure intervals and demarcate one moment from the next. It's this intricate neural symphony that transforms a chaotic barrage of sensory inputs into the orderly narrative we recognize as our life's timeline. The most compelling proof that this timeline is a constructed artifact and not a direct readout of reality comes from experiments where scientists directly manipulate this neural machinery. Using non-invasive techniques like transcranial magnetic stimulation, or TMS, researchers can apply targeted magnetic pulses to specific brain areas, temporarily disrupting their normal function. In one remarkable experiment, when TMS was used to interfere with the prefrontal cortex, subjects' ability to judge the order of events was significantly impaired. They could still perceive individual moments, but their brain lost the ability to sequence them correctly, scrambling their personal timeline. Other studies have used direct electrical stimulation in patients undergoing brain surgery, and by stimulating certain regions, they can evoke incredibly vivid and detailed memories, making the subject feel as if they are reliving a past event in real time. These interventions show that the flow of time is not a passive reception of an external signal, but an active, fragile process generated by the brain, a process that can be paused, sped up, rewound, or corrupted with the right kind of nudge. This neural construction also explains the bizarre and subjective elasticity of time we all experience. During a sudden, frightening event like a car crash, the well-documented phenomenon of time seeming to slow down occurs not because the world decelerates, but because the brain enters a state of hypervigilance. The amygdala, the center for fear and emotion, becomes highly active and triggers the brain to recruit more resources to record the event. It starts gathering sensory data at a much higher resolution, like a camera switching to a high-speed mode. This results in a denser, more detailed memory of the event. When you recall it later, the sheer amount of information packed into those few seconds makes it feel, in retrospect, like the event lasted much longer than it actually did. Conversely, when you're bored or performing a monotonous task, your brain isn't forming many novel memories, creating a sparser timeline that feels, in hindsight, like it shrank or flew by. When we place these neurological findings alongside the revelations from physics, a powerful and coherent picture begins to emerge, bridging the gap between the subjective and the objective. Physics tells us the fundamental laws are silent on time's direction, and cosmology suggests the arrow is a cosmic accident born from a low entropy beginning. Neuroscience now shows us the mechanism by which that cosmic accident is translated into personal experience. The brain is a physical system operating within the universe's thermodynamic gradient. It consumes energy, takes in ordered sensory information, and produces disordered waste heat, increasing entropy with every thought and memory. In doing so, it becomes a localized biological amplifier of the universe's statistical arrow. The brain doesn't detect time's flow, it instantiates it. It is a complex organ that has evolved to mirror the external increase of entropy in its internal processing, creating a story of cause and effect that is essential for survival. The now we feel is not a slice of an external timeline, but the brain's best guess at integrating sensory information to create a stable, usable model of reality. This interdisciplinary insight leads to a staggering proposition. the one-way nature of time might have no independent existence outside of systems that process information in this irreversible way. For a rock or a star, entities that do not construct a conscious timeline, the distinction between past and future may be utterly meaningless. They simply exist unchangingly at all points in the block universe. The flow is not a property of the space-time they reside in, but a property of a complex observer within it. This suggests that physics may never find a fundamental arrow of time in its equations because it's not there to be found. Instead, the arrow is a phenomenon that emerges at the level of chemistry, biology, and ultimately consciousness. It is a story that certain complex systems tell themselves. The final, crucial step in this journey is to find physical corroboration, to design experiments that can test whether the laws of physics truly are blind to this directionality once all cognitive observers are removed from the equation, pushing our understanding from a compelling psychological model toward a complete, observer-independent theory of reality. This philosophical stance, known as eternalism, presents a view of reality that is as beautiful as it is disorienting. It proposes that the past, present, and future are not sequential stages but fixed locations within a single, unchanging structure often called the block universe. In this model, your first birthday, the moment you are experiencing right now, and every event that will ever happen to you are all equally real. They don't pop in and out of existence. They simply are, eternally occupying their specific coordinates in the vast expanse of spacetime. This isn't just a metaphor, it's a direct interpretation of Einstein's theory of relativity, which seamlessly blends the three dimensions of space with the one dimension of time into a single, four-dimensional continuum. Within this continuum now loses its universal status. What you perceive as the present moment might be the distant past for an astronaut traveling at near light speed or the far future for someone orbiting a black hole. The concept of a universally agreed upon now shatters, leaving in its place a reality where every moment exists in a state of permanent, frozen completeness. To grasp how this works, consider a simple yet profound consequence of relativity known as the relativity of simultaneity. Imagine two lightning bolts striking the ground, one at the front and one at the back of a moving train. An observer standing on the platform, perfectly midway between the points of impact, sees both flashes of light at the exact same instant. For this person, the two strikes are simultaneous. However, an observer sitting in the exact middle of the train car is moving toward the light coming from the front strike and away from the light coming from the rear strike. Because light speed is constant for all observers, this person will see the flash from the front first and the flash from the rear a split second later. For them, the events were not simultaneous. Crucially, according to relativity, both observers are correct. There is no privileged frame of reference, no cosmic referee to declare one perspective right and the other wrong. This demonstrates that the notion of now is not an absolute fact of the universe but is relative to the observer's state of motion. If you cannot even define a universal present, then the idea that only the present is real becomes philosophically untenable. The past and future must be granted the same ontological status. They are just as real, just located in a different part of the four-dimensional landscape. This radically undermines our most intuitive experience, the feeling of a moving now, a present moment that seems to advance relentlessly from the past into the future, like a spotlight scanning across a stage. Eternalism suggests this spotlight is an illusion generated by our own consciousness. The stage, the entire block universe, is already fully lit. Every actor is frozen in their precise position, every line of dialogue already spoken. Our conscious awareness is not a spotlight moving through time. It is more like a process that sequentially illuminates or accesses one frozen moment after another along our personal world line. We don't move through time, we extend through it. The flow is not a property of the universe, but a property of how we, as conscious beings with memory and anticipation, experience our journey through this static structure. The arrow of time, from this perspective, is not an objective feature of the cosmos, but a subjective feature of our point of view within it. If this is true, it invites us to see our lives and our place in the cosmos in an entirely new light. We are not transient flashes in the pan, here for a brief moment before vanishing into nothingness. Instead, we are four-dimensional worms, or perhaps more elegantly, timeless sculptures stretched across the decades. Every joy you have ever felt, every moment of sorrow, every quiet afternoon, and every heart-pounding adventure is permanently and indelibly real, forever a part of the cosmic fabric. Your childhood self is not gone. They are eternally present at their coordinates in space-time, just as you, right now, are eternally present at yours. This can be a deeply comforting thought, as it confers a kind of immortality on every moment of our existence. It can also feel strangely fatalistic, as it implies that every choice we believe we are making has, in a sense, already been made. Our journey is one of discovery, not creation. We are reading our story, not writing it. This challenges our deepest notions of free will and destiny, forcing us to reconcile our powerful inner sense of agency with a universe that appears from a God's eye view to be a completed masterpiece. But if the arrow of time is indeed a local phenomenon, a consequence of our universe's incredibly specific and low entropy beginning, then we are forced to ask a question that pushes the boundaries of cosmology itself. What if our Big Bang wasn't the only one? What if our universe, with its particular set of physical laws and its specific arrow of time, is just one bubble in a vast, frothing cosmic ocean of universes, each with its own unique properties? This is the realm of the multiverse hypothesis, and it completely transforms the mystery of time from a puzzle about our local cosmos into a question about a much grander and potentially more bizarre meta-reality. The most developed scientific framework for a multiverse comes from the theory of cosmic inflation. This theory proposes that right after the Big Bang, the fabric of spacetime itself underwent a period of incredibly rapid, exponential expansion, smoothing and stretching the universe to the immense scale we see today. But a fascinating implication of many inflationary models is that this expansion may not have been a one-time event. Instead, it could be eternal. The driving energy field behind inflation, the inflaton field, might not decay everywhere at once. While it decays in our patch of reality to form our familiar universe, it could continue inflating elsewhere, constantly giving birth to new pocket universes in an endless, self-replicating process. Each of these bubble universes pinches off from the inflating background with its own random set of physical constants, determined by how the local inflaton field settled. This is where the arrow of time becomes a lottery ticket. The initial entropy of a universe is not preordained. It's a product of its specific birth conditions. In this eternal inflation scenario, an infinite number of universes are born. Some might burst into existence in a state of maximum entropy, a hot, disordered mess from the very beginning. In such a place, there would be no thermodynamic gradient to drive change, no clear distinction between past and future. Time, as we understand it, would be meaningless. Other universes might be stillborn, collapsing instantly or failing to form any structures at all. And then there are universes like ours, winners of the cosmic lottery, born with just the right, incredibly low entropy configuration to set off a 13.8 billion year chain of events, complete with a clear, relentless arrow of time. In this vast multiverse, our experience of time's flow is not a universal law. It is a local byproduct, a fortunate accident that allowed for the emergence of complexity, planets, and life. String theory, another ambitious attempt to unify all physics, offers its own version of a multiverse known as the string landscape. This theory suggests there are perhaps 10 to the 500 different possible stable configurations for the extra dimensions it proposes. Each configuration corresponds to a universe with a different set of physical laws and constants. Within this unimaginably vast landscape of possibilities, every conceivable arrow of time is represented. Some universes might have time that behaves exactly like one of our spatial dimensions, with beings who can move back and forth along it as easily as we walk left and right. Others might have multiple time dimensions, leading to a reality of such complexity that our linear brains couldn't begin to fathom it. And yes, some universes would have an arrow of time that is the exact reverse of our own. Imagine a universe where time runs backward relative to ours. This doesn't mean people would be walking backward or talking in reverse. From the perspective of an observer inside that universe, their experience would feel just as normal and linear as ours does to us. They would remember what we would call their future and anticipate what we would call their past. A cup would, from our external viewpoint, unshatter and leap from the floor into their hand, but from their internal viewpoint, it would simply be a normal action of picking up a whole cup. The psychological arrow of time, the formation of memories, the sense of causality, would be inextricably linked to the thermodynamic arrow. They would be born old and die young, but they would experience it as growing younger and then being born, with their memories forming of the events in their future. Their entire history would be, from our perspective, a perfectly coherent movie played in reverse, but for them, it would be the only reality they had ever known. This multiverse perspective is the ultimate demotion for time's arrow. It suggests that the one-way flow we consider to be the most fundamental aspect of our existence is not written into the laws of physics at all. It is a contingent feature, a parochial detail of our particular cosmic neighborhood. It is an environmental condition, like the oxygen in our atmosphere, essential for our kind of life but utterly absent in the void between planets. By expanding our view to encompass the possibility of other universes, we see that the puzzle of time is not about finding a law that creates the arrow, but about understanding why we happen to inhabit a universe that has one. This doesn't make our experience any less real, but it does frame it within a context of breathtaking vastness and variety, suggesting that the true nature of reality is far stranger and more diverse than our singular, time-bound perspective could ever allow on its own. We often picture human history as a grand, upward march, a story of continual improvement from primitive beginnings to our modern, sophisticated present. This narrative of progress is so deeply embedded in our culture that it feels like a natural law, as undeniable as gravity. We chart timelines that move from left to right. Our history books divide the past into neat, progressive eras like the Stone Age, the Bronze Age, and the Industrial Age, implying a clear and inevitable trajectory toward a better tomorrow. But what if this sense of moving forward through time is not an objective feature of history, but a story we've chosen to tell ourselves? A powerful cultural lens through which we view a much more chaotic and ambiguous past. This compelling idea of linear progress is largely a product of the 18th century European intellectual movement known as the Enlightenment. Thinkers of this period, buoyed by scientific revolutions, began to envision human history not as a cyclical pattern or a slow decline from a golden age, but as a linear path of intellectual and moral advancement. They believed that reason, science, and education would inevitably lead humanity toward greater freedom, prosperity, and perfection. This was a radical and optimistic departure from previous worldviews, and it provided the foundational script for the modern world story about itself. It gave us the powerful and often unchallenged belief that the future will be better than the past and that we are always moving in that positive direction. However, the field of historiography, the study of how history is written, reveals how this arrow of time is actively imposed on events, not discovered within them. Historians are not simply neutral collectors of facts. They are storytellers who must select, emphasize, and connect disparate events into a coherent narrative. This process inevitably involves crafting a plot with a beginning, middle, and end, which creates a sense of direction and purpose that the raw events themselves do not possess. For instance, the history of technology is often told as a seamless sequence of brilliant inventions, each one building on the last. This narrative conveniently overlooks the countless dead ends, forgotten technologies, and periods of profound knowledge loss that also define our past. The timeline smooths over the chaos, creating a clean arc of progress where one may not inherently exist. We can see this narrative construction at work in the very language we use. We talk about advanced civilizations and developing nations, implying a single ladder of progress that every society is supposed to climb. We refer to certain ideas as ahead of their time and others as backward, using spatial metaphors of forward and backward motion to describe what are simply different cultural or temporal contexts. This language doesn't just describe progress, it actively creates and reinforces the illusion that time itself has a built-in direction toward a specific goal. It turns the complex, multidirectional tapestry of human experience into a simple, one-way street. This societal arrow of time, crafted through history and language, creates a fascinating parallel to the puzzle in physics. Physics found a contradiction between time's symmetric laws and our irreversible experience, ultimately locating the arrow in the specific low-entropy initial conditions of the universe. In a similar way, our cultural experience of historical time shows a contradiction between the chaotic, non-linear nature of events and our powerful narrative of linear progress, ultimately locating the arrow in the specific way our society chooses to structure its stories. Both point to the same profound conclusion. The flow of time is not something we detect in the world, but something we project onto it. It is a tool for creating meaning out of chaos. By deconstructing the idea of progress, we begin to see that time's flow is not an inherent truth of the cosmos, but a profoundly human tool for making sense of our existence. We are storytelling creatures, and a story requires sequence, causality, and direction. We cannot help but weave the random events of our lives and our collective past into a narrative with a plot. This narrative instinct is so powerful that we mistake the structure of our story for the structure of reality itself. We conflate the arrow of narrative with an arrow of time, believing that because our stories have a beginning, middle, and end, the universe must too. This realization doesn't diminish the importance of our stories, but it does free us from being enslaved by a single, dominant narrative. It allows us to consider that other cultures, with their cyclical concepts of time or their focus on eternal, recurring patterns, might be capturing a different and equally valid aspect of reality. Our linear progression is just one way to tell the tale, a chapter in a much larger book where the very idea of chapters might be another comforting illusion. Long before physicists ever wrote an equation, artists and writers were already dissecting the nature of time, not with mathematics, but with intuition and emotion. They have always served as our cultural scouts, venturing into the metaphysical wilderness and returning with maps of territories that science is only now beginning to formally explore. Their work provides a different kind of evidence for time's fluidity, not data from a particle accelerator, but a profound resonance in the human soul that challenges the tyranny of the clock. Consider Salvador Dali's iconic painting, The Persistence of Memory, with its limp, melting watches draped over a barren landscape. This isn't just a surreal image, it's a philosophical argument made visual. Those soft clocks are a direct assault on the Newtonian idea of time as a rigid, mechanical constant. Dali portrays time as subjective, malleable, and organic, a substance that warps and drips under the weight of dreams, memory, and desire. He captures the exact same feeling we all know so well, that an hour in a dull meeting can feel like an eternity, while an afternoon with a loved one can feel like a fleeting minute. This artistic intuition, that time is relative to consciousness, eerily predates and mirrors Einstein's revolutionary scientific conclusion that it is relative to motion and gravity. This exploration of time's elasticity is even more pronounced in literature, where authors can manipulate the very structure of narrative to mirror their themes. A straightforward, chronological tale reinforces a linear, cause and effect view of time, but many of our greatest writers deliberately shatter this structure to reveal a deeper truth. In her novel, Mrs. Dalloway, Virginia Woolf masterfully confines the entire story to a single day in London. Yet, within that tight frame, the consciousness of her characters spirals outward, dipping freely into memories from decades past and anxieties about the future. The narrative present is not a point on a line, but a rich tapestry woven from threads of memory, sensation, and anticipation. Woolf shows us that a human mind does not experience time in a straight line. It exists in a constant state of flux, where a single scent can instantly transport us to our childhood, collapsing years into a single moment. This literary technique, known as stream of consciousness, doesn't just tell us about time's fluidity. It forces us to experience it firsthand as we read, blurring the lines between past, present, and future in our own minds. This creative defiance of linearity finds a modern, sprawling expression in works like Christopher Nolan's film Inception, which presents time as a layered architecture where decades can pass in a dream while only minutes elapse in reality, or in Audrey Niffenegger's novel The Time Traveler's Wife, where a relationship unfolds entirely out of sequence, highlighting that love and emotion connection can exist outside of chronological order. These stories do more than entertain, they act as training grounds for our perception. They prepare us intellectually and emotionally for the possibility that the universe might not operate on a single, simple timeline. When a character meets their future self or a narrative loop closes on itself, it creates a cognitive dissonance that is strangely satisfying. It feels true in a way that a strictly linear story often does not, suggesting that our deepest intuitions have long been aware of time's trickery, even if our rational minds have been slow to catch up. The profound connection between these artistic explorations and the scientific ideas we've discussed is anything but coincidental. Both are grappling with the same fundamental mystery from different angles. The physicist uses the language of mathematics to describe a block universe where all of time exists simultaneously. The artist uses the language of symbol, narrative, and image to evoke what that might feel like. Dali's melting clocks are a visceral, emotional representation of the relativistic warping of spacetime. A nonlinear novel is a narrative analog of the quantum foam, where causality is fuzzy and events don't have a strict before and after. Art provides the cultural and emotional proof for concepts that physics arrives at through logic and experiment. It reassures us that the universe described by equations is not a cold, alien place, but one that resonates with the deepest patterns of human thought and creativity. The artist's canvas and the physicist's blackboard are both maps of the same mysterious territory, one drawn with emotion and the other with algebra, and each is more complete with the other as a guide. Engaging with these works is more than a passive aesthetic experience. It is an active participation in the mystery of time. When we stand before a painting that warps chronology or lose ourselves in a book that scrambles narrative, we are not just being told that time is an illusion. We are feeling it in our gut. This visceral understanding complements the intellectual journey of physics, grounding abstract theory in the soil of human experience. It allows us to hold two truths at once: that our lives are a beautiful, poignant story unfolding in a sequence of irreplaceable moments, and that this entire story may already be complete, a timeless sculpture in the grand museum of the cosmos. Art doesn't solve the puzzle of time, but it deepens the wonder, transforming a scientific paradox into a personal and deeply human mystery that we can all appreciate, regardless of our familiarity with quantum mechanics or entropy. Imagine a universe where the fundamental script of reality is flipped, where the very definition of before and after loses all meaning. In this bizarre cosmos, the second law of thermodynamics runs in reverse. Entropy doesn't increase towards disorder, it consistently decreases towards order. The most familiar processes of our existence would unfold in a breathtakingly alien manner. A shattered wine glass lying in pieces on the floor would suddenly leap upward, every shard finding its perfect neighbor, fusing seamlessly back into a pristine, whole vessel before landing gently on the table. Puddles would gather themselves from the soil, defying gravity to coalesce and leap back into their clouds. Forests would not grow from seeds but would instead condense from the atmosphere, their trees shrinking year by year into saplings before retreating into the earth, leaving no trace behind. The experience of life in such a universe would be the ultimate mind-bending paradox. Beings there wouldn't be born young and grow old. They would be born old, with a lifetime of memories already intact but no knowledge of their future. They would experience their lives in reverse, growing younger and more vigorous with each passing day. A person would begin their life at their physical and mental peak, perhaps as a revered elder, and over the years they would gradually shed their knowledge and experience, their body growing stronger and more supple until they eventually regressed into infancy and finally vanished from existence. Their memories would not be of the past but of the future, a future that, from our perspective, has already happened. They would remember tomorrow's conversations with perfect clarity, but have no idea what they will say or do today. Causality, the unbreakable chain that anchors our reality, would be completely inverted. In this world, a bruise would appear on your skin before you bumped into the table, and the sound of a scream would echo through the air before the terrifying event that caused it. Now, here is the most startling part of this thought experiment. Such a universe is not necessarily forbidden by the fundamental laws of physics. The equations governing motion, electromagnetism, and even quantum mechanics are largely time-symmetric. A video of planetary orbits or colliding particles looks physically plausible whether played forward or backward. The problem isn't with the laws themselves, but with the initial conditions. A time-reversed universe would require a starting point of incredibly high entropy, a state of maximum disorder, from which it would then evolve towards ever greater order and structure. This is the exact opposite of our own cosmos, which began in a state of incredibly low entropy. The arrow of time, it seems, is not an absolute dictate written into the cosmic code. It is a contingency, a direction inherited from a single, specific moment at the birth of our universe. By entertaining this reversal, we perform a powerful act of intellectual liberation. We loosen time's grip on our imagination, allowing us to see it not as an immutable constant but as a variable, a parameter that could, in principle, be set differently. This exercise forces us to distinguish between what is logically possible and what is probabilistically likely. A universe with a reverse arrow is logically consistent with the underlying laws, but it is astronomically improbable because it requires that highly ordered, low entropy state to exist in the far future, acting as a mysterious attractor that pulls the entire cosmos toward it. This imaginative journey doesn't just show us a weird alternative reality. It profoundly underscores that our own experience of cause preceding effect, of memory defining the past, is not a necessary truth of existence. It is a gift, a specific and incredibly rare starting point that gave our universe a history, a narrative, and ultimately, the possibility of beings like us who can ponder its beautiful, fleeting strangeness. Now, if our most advanced theories are whispering that time might be an emergent property, not a fundamental one, then the machines we are building to test those theories are starting to shout it from the rooftops. We are entering the era of quantum computing, a technology that doesn't just calculate with ones and zeros, but harnesses the very phenomena that make time's arrow seem so suspicious: superposition and entanglement. Unlike a classical computer which processes information in a strict, sequential series of steps, a quantum computer operates in a realm where multiple possibilities are explored simultaneously. A qubit, the fundamental unit of quantum information, isn't just a 1 or a 0. It can be both at the same time, a state of pure potentiality that exists outside our classical notion of a single, determinate timeline. This profound difference is perfectly illustrated by a revolutionary algorithm like Shor's algorithm, designed to factor large numbers. For a classical computer, factoring a massive number is a Herculean task that requires checking possible factors one after the other, a process whose time requirement grows exponentially with the size of the number. It's a sequential march through possibility space, a perfect metaphor for our one-way experience of time. But a quantum computer running Shor's algorithm takes a breathtaking shortcut. It doesn't check factors sequentially. It uses the power of superposition to effectively check all potential factors at once. Through a carefully orchestrated series of quantum operations, it amplifies the correct answer and cancels out the wrong ones, arriving at the solution not through a laborious step-by-step journey, but almost as if by magic, by seeing the entire answer space instantaneously. The process isn't just faster, it's ontologically different. It sidesteps the classical chain of cause and effect, achieving its result in a way that feels less like a computation and more like a revelation, a glimpse into a reality where sequence is optional. This technological marvel forces us to ask a staggering question. If a quantum computation can find an answer without following a strict temporal path, what does that say about the nature of the answer itself? It suggests that the solution was, in a sense, always there, embedded in the mathematical fabric of the universe, waiting to be uncovered not through laborious step-by-step work, but through a kind of correlation, a sudden alignment of quantum states that reveals a timeless truth. This is a powerful hint that the universe might not compute its future state from its past state in the way we imagine. Instead, the entire history of events might be more like a vast, pre-existing pattern of correlations, and our perception of time is simply our consciousness tracing a single, linear thread through that immense and intricate tapestry. The ultimate implication of this is almost too strange to contemplate. If we fully master quantum mechanics and can perfectly control and reverse quantum states, could we theoretically run a computation backwards? Not just undo a calculation, but actually reverse the flow of information processing itself. A classical computation is fundamentally irreversible. When a logic gate takes two inputs and produces one output, information is lost, entropy increases, and that operation cannot be perfectly undone. This is Landauer's principle in action, and it's a direct manifestation of the thermodynamic arrow of time. but a perfectly coherent quantum computation, in theory, can be reversible. Because it preserves all quantum information in a delicate web of superpositions and entanglements, it might be possible to run the entire process in reverse, from the answer back to the question, unscrambling the egg with perfect fidelity. A machine that could achieve this wouldn't just be a calculator. It would be a physical demonstration that the underlying laws governing its operation are truly ambivalent about the direction of time. Building such a device would be the most profound experimental challenge to our experience of time's flow imaginable. It wouldn't just be a philosophical argument about entropy or the block universe. It would be a tangible, physical system in a laboratory that processes information without a clear, irreversible arrow. While this wouldn't allow us to send messages to the past or change history, it would provide concrete, empirical evidence that the one-way street we all experience is not a fundamental feature of reality, but a large-scale emergent property, a compelling story that emerges from countless interactions, but a story nonetheless. The quantum computer, therefore, is more than just a next-generation tool. It is a probe into the deepest nature of causality and time itself, a machine that might one day prove the ultimate illusion not through equations but through experimental fact. But if the fundamental laws are so ambivalent, and if our psychological experience is a constructed narrative, where does this powerful, unidirectional push actually come from? To find a truly physical source for time's arrow, we must turn to the force that literally shapes the cosmos, gravity. Einstein's general theory of relativity revolutionized our understanding by fusing space and time into a single, dynamic fabric called spacetime, which curves and warps in the presence of mass and energy. This curvature is what we experience as gravity. A planet orbits a star not because it's pulled by a mysterious force, but because it's following the straightest possible path, a geodesic, through the curved geometry of spacetime around that star. Now here's the crucial question. Does this bending of spacetime itself possess a built-in arrow? Does gravity care about the difference between past and future? On the surface, Einstein's equations, like those of Newton and quantum mechanics, are time-symmetric. A video of a planet's orbit or a star's graceful dance around another star would look perfectly normal whether played forward or backward. There's no obvious preference. However, gravity introduces something new and profound to the conversation: the relentless and irreversible tendency to create order out of chaos. This might sound counterintuitive. We usually associate increasing entropy with disorder, like a scattered deck of cards. But in the realm of gravity, the most disordered state isn't a scattered mess. It's a featureless, thin soup of particles evenly distributed throughout space. The most ordered, low-entropy state is actually a highly structured one, a massive, dense object like a star or a black hole. Think of the early universe revealed by the cosmic microwave background. It was incredibly smooth and uniform, a state of very high entropy for gravity. But this uniformity is unstable. Under the relentless pull of gravity, tiny fluctuations in density were amplified over billions of years. Matter began to clump together, forming galaxies, stars, and planets. This process of structure formation represents a dramatic decrease in gravitational entropy. The universe is moving from a smooth, high-entropy state to a lumpy, structured, low-entropy state. This is the exact opposite of the thermodynamic arrow we see with shattered glasses and melting ice cubes. So, we have two competing arrows. Thermodynamics says disorder increases, while gravity says order increases. This isn't a contradiction. It's the universe's way of driving complex evolution. The thermodynamic arrow ensures energy flows and things happen, while the gravitational arrow builds the grand stages, the galaxies and stars where those things can occur. The most extreme manifestation of gravity's power is, of course, the black hole. These cosmic anomalies are not just objects. They are regions where the curvature of space-time becomes so severe that not even light can escape. And they play a fascinating role in the story of time. According to the famous Hawking radiation theory, black holes aren't entirely black. Due to quantum effects at their event horizons, they slowly evaporate, emitting particles and energy over unimaginable timescales. This process is incredibly significant because it appears to be fundamentally irreversible. Information, the specific arrangement of matter and energy that fell in, seems to be lost forever, scrambled into a form of thermal radiation. This black hole information paradox suggests that black holes might be the ultimate engines of entropy increase, the most efficient converters of order into disorder in the entire universe. Their existence and eventual evaporation could be the ultimate reason why the cosmic arrow of time points so steadfastly in one direction. This gravitational perspective opens the door to some of the most daring cosmological theories. Sir Roger Penrose, for instance, proposes a breathtakingly beautiful model called conformal cyclic cosmology. In this vision, the ultimate fate of our universe, a cold, empty expansion into maximum entropy, known as the heat death, is not the end. Penrose suggests that as the universe expands and becomes utterly vast and empty, the concept of scale itself loses all meaning. In this strange, conformally invariant state, a universe that has reached maximum entropy becomes mathematically identical to a universe at the moment of the Big Bang, which had minimum entropy. This allows for a seamless transition, a cosmic reset where the endless future of one universe becomes the hot, dense beginning of the next. In this cyclical model, the arrow of time is not a one-way street. It is reborn with each new aeon. Beings in the next cycle would perceive our distant future as their Big Bang, their arrow of time pointing in the opposite cosmological direction from ours, yet feeling just as absolute and real to them. By weaving gravity into the narrative, we see that time's flow is not a solitary phenomenon, but is deeply entangled with the geometry and evolution of the entire cosmos. It is not a backdrop against which the universe plays out. It is a dynamic player in the drama, shaped by mass and energy, and in turn shaping their destiny. Gravity provides the cosmic engine that drives the universe from a simple, smooth beginning toward ever greater complexity and structure, all while ultimately ensuring, through the grim mechanics of black holes, that the overall tide of entropy continues to rise. This doesn't solve the mystery of time's arrow. It deepens it magnificently, showing that our journey from past to future is woven into the very fabric of space-time, a fundamental thread in the unfolding story of the universe itself. So if time's arrow is woven into the cosmos by gravity and thermodynamics, we must turn our attention to the most complex and ordered structures that have emerged from this process, living things. Every living organism, from a towering redwood tree to a microscopic bacterium, is a powerful testament to time's direction. We are born, we grow, we reproduce, we age, and we die in a sequence that feels as absolute and undeniable as the law of gravity itself. This biological arrow of time is the most intimate one we know, written into our very cells and felt with every beat of our hearts. Yet, is this profound experience of a one-way journey a fundamental property of life itself? Or is it merely a compelling echo of the deeper physical processes that gave rise to us? To answer that, let's look at the life cycle of a simple organism. A seed germinates, sending a shoot upward toward the sun, and roots downward into the soil. It matures, photosynthesizes, and eventually flowers, producing new seeds before its leaves brown and fall, returning its matter to the earth. This entire process is a local and spectacular battle against the thermodynamic tide. The plant takes in disordered molecules, carbon dioxide, water, minerals, and using energy from sunlight, assembles them into the highly ordered, complex structure of its own body. It creates a pocket of stunningly low entropy, a temporary oasis of organization in a universe sliding toward disorder. But this fight is ultimately a losing one. The maintenance of this order requires a constant flow of energy. When that flow stops, decay sets in. The intricate molecules break down, and the plant structure succumbs to the relentless pull of entropy, its ordered carbon becoming food for decomposers and eventually dispersing back into the environment. Life doesn't defy the second law of thermodynamics. It temporarily channels it, acting as a complex intermediate step on the universe's overall journey to higher disorder. This brings us to the grandest biological narrative of all, evolution. The story of life on Earth is often told as a majestic arrow of increasing complexity, from the first simple replicating molecules in a primordial soup to the breathtaking diversity and sophistication of life we see today. It's a story that seems to have a clear direction and therefore a clear arrow of time, but we must be careful here. This increase in complexity is not driven by some mysterious internal force pushing life upward. It is an emergent property, a side effect of the brutal, mindless engine of natural selection operating within the constraints of a universe with a thermodynamic arrow. Random mutations create variation, and environmental pressures select for adaptations that best allow organisms to survive and reproduce. Over deep time, this process can and does build staggering complexity, but it is not its goal. A bacterium is no less evolutionarily successful than a human. It is simply a different solution to the problem of survival, honed by billions of years of selection in its niche. The perceived arrow of evolution is not a fundamental direction of time but a contingent history, a specific path taken on a vast landscape of possibilities, entirely dependent on our planet's unique conditions and countless chance events. The experience of time within our own consciousness adds another layer to this illusion. Our brains are not passive cameras recording a linear timeline. They are active, predictive engines constantly constructing a model of the world. They take a chaotic stream of sensory data, sights, sounds, smells, and after a slight delay, stitch it together into a coherent story of a flowing present. This specious present, a window of about 2 to 3 seconds, is the fundamental unit of our lived time. Our memory then files these moments away, creating a personal history. This entire apparatus creates the powerful, unshakable feeling that we are moving forward through time. But this is a brilliant cognitive trick, a user interface for reality. It is an adaptation that was ruthlessly selected for because it is incredibly useful for survival. An organism that could remember where it found food yesterday and anticipate where a predator might be tomorrow had a monumental advantage over one that could only react to the immediate now. Our biological arrow of time, then, is not a detection of a cosmic flow but a construction, a story our brain tells us to make sense of cause and effect, to learn from the past and to plan for the future. Therefore, the relentless march we feel from birth to death is not evidence of a fundamental temporal force within biology. It is a magnificent and poignant consequence. The chemistry that powers our cells is driven by irreversible reactions that increase entropy. The information in our DNA is copied and passed on with slight errors, providing the variation for natural selection. Our consciousness constructs a linear narrative to navigate the world. Every aspect of life's arrow is built upon and entirely dependent on the deeper arrows of physics and thermodynamics. Life is not the source of time's direction. It is one of its most beautiful and complex expressions. We are not sailing against the current. We are intricate patterns formed by the current itself, temporary eddies in the cosmic river, experiencing the flow from our own unique and limited perspective. Think about the last time you checked the clock, waiting for a meeting to end or for a loved one to arrive. That steady, predictable tick-tock feels like the most reliable thing in the world, a universal metronome keeping pace for everyone, everywhere. We structure our entire lives around this assumption that a second for you is a second for me, no matter where we are or what we're doing. This deeply ingrained belief that time is absolute and universal is perhaps the most common myth of all, a ghost of Newtonian physics that still haunts our daily perception. But what if this bedrock certainty is nothing more than a comforting illusion, shattered over a century ago by a young patent clerk named Albert Einstein? His theory of relativity delivered a knockout blow to the idea of a single, universal clock. Einstein revealed that time is not a rigid backdrop. It's a flexible dimension, intimately woven together with space into a single fabric called space-time, and this fabric can stretch and warp. The rate at which time passes depends entirely on two things: your speed and your proximity to gravity. This isn't a tiny, theoretical effect. It's a measurable reality that has profound consequences. Consider the famous twin paradox. Imagine one twin stays on Earth while the other embarks on a journey into deep space at a significant fraction of the speed of light. For the traveling twin, time would literally slow down relative to the twin on Earth. Upon returning after what felt like a few years, the astronaut might step out of the ship to find their Earth-bound sibling has aged decades. Their lived experiences, the number of heartbeats, the memories formed, all would be out of sync. Both experiences of time are equally real from their own perspectives, proving there is no single, privileged now for the entire universe. We even see a much gentler, everyday version of this relativity at work with time zones. When it's noon for you, bright and sunny, a friend a few thousand miles away is already finishing their dinner in the evening darkness. You both exist in the same present moment, yet your clock time is different. This is a social agreement that hints at a deeper truth, that the present is not a global event but a local one. Relativity takes this concept and pushes it to its logical, mind-bending extreme, showing that even the sequence of events can be relative. If two events are separated in space, different observers moving at different speeds can disagree on which happened first, provided the events are not causally connected. This shatters any remaining notion of a universal, flowing river of time that everyone shares. Another powerful myth is the idea of the future as a blank page, an unwritten story full of possibility, while the past is a fixed, unchangeable book sitting on a shelf. This feels intuitively true. We can't go back and change our actions, but we feel we can shape what comes next. Yet, if we take the block universe model suggested by relativity seriously, this distinction begins to blur. In this view, the future may be just as fixed and real as the past. It's simply a part of the universe we haven't observed yet. Think of your own life not as a story being written, but as a novel that already exists in its entirety. You are simply turning the pages, experiencing the narrative in sequence. From a point outside of time, the final chapter is just as complete and real as the opening sentence. This doesn't negate our feeling of free will or the importance of our choices. It simply suggests that those choices are a part of the fixed structure of the whole story. The future feels open because we are, by our very nature, trapped in the process of discovering it. These misconceptions of absolute time and an open future are the biggest hurdles to accepting the radical ideas we've been exploring. We cling to them because they are the very framework of our conscious experience. letting them go can feel deeply unsettling, like the ground giving way beneath your feet. But this demystification is a necessary and liberating step. It's not about making the universe feel colder or more deterministic. It's about expanding our understanding of what reality might actually be. By clearing away these outdated intuitive models, we make room for a much stranger, richer, and more fascinating picture to emerge, one where time itself might not be a fundamental ingredient of the cosmos, but a spectacularly persistent and convincing side effect of our particular point of view. So where do we go from here? If the nature of time remains one of physics' greatest unsolved puzzles, what are the actual experiments, the concrete steps that could push our understanding forward? The quest is moving out of the realm of pure philosophy and into the domain of hard, testable science, with several thrilling frontiers leading the charge. One of the most powerful tools we have is, of course, the Large Hadron Collider. While it's famous for discovering the Higgs boson, its work is far from over. Researchers are now using this colossal machine to probe the very edges of our theories, searching for particles or interactions that might reveal a crack in time's facade. For instance, by studying the behavior of certain exotic particles with unimaginable precision, physicists hope to find even the slightest violation of time reversal symmetry. Finding definitive proof that certain subatomic processes are not perfectly reversible would be a monumental discovery, suggesting that the arrow of time might be woven into the universe's most fundamental rulebook after all, not just a large-scale statistical outcome. Beyond smashing particles together, another frontier involves building increasingly precise clocks, not to tell time better, but to use time itself as a sensor. The latest atomic clocks are so astonishingly accurate that they can detect differences in the passage of time due to a change in elevation of just a few centimeters, a direct test of Einstein's time dilation from gravity. By placing networks of these ultra-precise clocks in space or connecting them across continents, scientists aim to create a kind of time telescope to observe the fabric of space-time itself. They could look for tiny, rhythmic fluctuations in the flow of time that might be caused by passing gravitational waves from the early universe, or even stranger phenomena. These clocks are so sensitive they might one day detect the faint quantum fuzziness of space-time, a direct signature that time is not a smooth, continuous background, but is made of discrete, grainy units at the Planck scale, a finding that would revolutionize our entire conception of reality. On the theoretical side, one of the most radical and promising ideas is the holographic principle. This concept suggests that our seemingly three-dimensional universe, complete with the flow of time, might actually be a projection of information encoded on a distant, two-dimensional surface, much like a hologram emerges from a flat sheet of plastic. In this mind-bending view, time doesn't exist on that fundamental two-dimensional boundary. It is an emergent property that only comes into existence when the higher dimensional universe is projected out. Think of it like watching a movie on a screen. The story has a beginning, middle, and end, a clear timeline. But that timeline isn't a property of the individual pixels on the screen. It emerges from the way those pixels are illuminated in sequence. If the holographic principle is correct, then time is that emergent story, and the real, fundamental laws of the universe are timeless, playing out on a boundary we cannot see. Proving this isn't about building a bigger telescope. It's about finding a precise mathematical correspondence between theories of gravity in 3 dimensions and quantum theories on a 2-dimensional surface, a puzzle that theorists are vigorously working on right now. This vibrant, multi-pronged attack on the problem means that the question of time's fundamental nature is anything but settled. It is a wide-open field, perhaps the final great frontier of classical physics. The next decade promises data that could tilt the scales decisively toward one of these incredible ideas. We might receive a clear signal from a particle collider, an unexpected reading from a quantum computer, or a mathematical breakthrough that finally unites gravity and quantum mechanics. What's truly exciting is that this isn't just an abstract debate for physicists in ivory towers. It's a journey that challenges the very core of our experience. Every new experiment, every theoretical advance, brings us closer to answering whether the river of time we all feel so deeply is the ultimate reality or the universe's most profound and beautiful illusion. The investigation is live, and the next chapter is being written in laboratories and on blackboards around the world right now. So here we stand at the end of our exploration, having gathered pieces of the puzzle from every corner of physics. We have the thermodynamic arrow, born from a cosmic lottery ticket, a universe that began in a state of exquisitely low entropy, setting off a chain reaction of increasing disorder that our brains interpret as the flow of time. We have the quantum realm, where the fundamental equations show a perfect indifference to past and future, and where phenomena like entanglement and delayed choice experiments actively fray the edges of our classical timeline, suggesting a reality where before and after are not rigidly defined. And we have the sobering architecture of relativity, which paints a picture of a block universe, a static, four-dimensional landscape where every event in history simply is, and our feeling of passage is a cognitive artifact, a story we tell ourselves. Individually, each of these perspectives is a powerful challenge to our intuition, but when you weave them together, their combined strength is overwhelming. They are not contradictory stories, they are different chapters of the same grand narrative, each providing a crucial piece of the explanation. The low entropy Big Bang provides the initial condition. The statistical mechanics of Boltzmann explains how that condition generates an overwhelming probability for change in one direction. Quantum mechanics reveals that the fundamental laws governing that change are themselves time-symmetric, and relativity provides the stage, the block universe upon which this entire drama is permanent. Etched, our consciousness, a product of this thermodynamic universe, then acts as the narrator, reading this single, frozen timeline in a sequential order and generating the inescapable feeling of a moving now. This synthesis points toward a reality that is, at its most fundamental level, timeless. The change we perceive is not happening within time. It is the very phenomenon that creates the illusion of time. The universe is a vast network of correlated events. The growth of entropy, the formation of memories, the consistent sequence of cause and effect we observe, these are not features of time itself, but features of our particular journey through an eternal structure. From a God's eye view outside the system, the distinction between the birth of a star and its death might be as meaningful as the distinction between the top and bottom of a mountain is to the mountain itself. They are just different locations in a grand, unchanging geography. This holistic view doesn't diminish the reality of our experience, it simply recontextualizes it. The urgency of a deadline, the ache of nostalgia, the thrill of anticipation, these feelings are no less potent, but understanding their origin allows us to hold two truths in our minds simultaneously. We can live fully within the river of our experience, while appreciating that the river itself might be the most magnificent and persistent mirage the universe has ever conjured. We are not just passive riders on the current of time, we are active participants in a timeless reality, and our journey, with all its joy and sorrow, is a permanent and indelible part of the cosmic landscape. So this profound journey through the laws of physics leaves us at a truly staggering crossroads. The relentless, one-way flow of time, which feels as undeniable as the ground beneath our feet, appears increasingly to be the universe's most convincing and pervasive illusion. It's not a fundamental current woven into the cosmos, but a magnificent trick, a story told by the statistical drive of entropy, constructed by our own consciousness, and made possible by a single, incredibly specific starting point some 13.8 billion years ago. From the timeless block universe of relativity to the fuzzy correlations of quantum mechanics, the evidence doesn't just hint. It mounts a compelling case that time's arrow is not a primary feature of reality but an emergent property, a side effect of our particular place within a much grander and more mysterious whole. This revelation does far more than just rewrite physics textbooks. It fundamentally transforms how we see our own existence. If the future is already just as real as the past, then the anxiety of what's to come loses its grip. If every moment of our lives exists eternally in the cosmic structure, then no experience is ever truly lost. This perspective doesn't erase the poignancy of our journey, it sanctifies it. It frees us from the tyranny of the clock, inviting us to stop merely counting the seconds and instead to sink into the depth and quality of each one. The urgency of a deadline, the warmth of a memory, the thrill of a first kiss, these aren't diminished. They are granted a kind of immortality, forever fixed as indelible coordinates in the vast expanse of space-time. We are not transient ghosts hurrying toward an end. We are timeless sculptures, our entire story already complete, and our consciousness is simply tracing its beautiful, predetermined path. Yet for all its philosophical power, this remains one of the great open questions in science. The next thrilling chapter in this story will be written not by theorists alone, but by experimentalists. The hunt is on for that definitive, physical proof, a clear violation of time symmetry in a particle decay, a gravitational wave signature from before the Big Bang, or perhaps a profound revelation from a quantum computer that processes information in a way that truly has no past or future. We stand on the precipice of discoveries that could finally tip the scales, moving this idea from a mind-bending possibility to an established fact of our universe. And that, perhaps, is the most exciting part of all. To question the nature of time is to question the very fabric of reality itself. It's a pursuit that pushes the limits of human understanding, blending the hardest of sciences with the deepest of philosophies. So I want to hear what you think. Does this idea resonate with you, or does it feel completely alien? Share your own perspective and your biggest questions down in the comments. Let's get a fascinating discussion going. If your mind feels expanded and you want to join us for the next deep dive into the mysteries of the cosmos, make sure to subscribe and hit that notification bell. Keep wondering, keep exploring, and remember, in a universe that might ultimately be timeless, every single moment we have is an incredible opportunity for discovery. If this journey through the nature of time has reshaped your perspective, showing you the universe from a startling new angle, then let that curiosity ripple outward. Hitting the like button is a fantastic way to signal that you value this kind of deep, mind-expanding content. And sharing this video is how you spark these fascinating conversations with friends and fellow thinkers. It's how we build a community of curious minds all exploring the cosmos' biggest questions together. By subscribing to the channel, you're not just getting more videos, you're ensuring your feed is regularly filled with journeys to the edge of our understanding, from the event horizons of black holes to the mind-bending possibilities of the multiverse. This is your invitation to stay on this path of discovery with us. Now, we genuinely want to turn the microphone over to you. This isn't a one-way lecture, it's the start of a dialogue. The nature of time is one of the most personal puzzles there is. It's the very fabric of our lived experience. So, what's your take? After all we've explored, does your gut tell you that time is a fundamental river we're all floating on? Or is it, as the physics suggests, a magnificent and persistent illusion constructed by our own minds? Do you find the block universe model liberating or utterly terrifying? Share your personal reflections, your biggest questions, or even your own theories down in the comments. That discussion below the video is where the real magic happens, where we can all learn from each other's perspectives. To make sure you're always part of the conversation the moment a new one begins, click that notification bell. It's the best way to ensure you're immediately alerted when we drop our next investigation into reality's grandest mysteries. Thank you for investing your time and your incredible curiosity here. Together, let's keep pulling on these threads, challenging assumptions, and unraveling the universe's most profound secrets, one